Oh, cool.
Brilliant. We are going to kick things off with Dr. Terry Fong, who is set to go. Everyone settle in, and I'll start the timer for you.
You can wait 10 minutes to start that. That's really fun.
Over to you.
Great.
Thank you.
All right, good afternoon, everybody. For those of you who I have not yet met in person, I'm Terry Fong. I'm the NASA Senior Scientist for Autonomous Systems. I lead what's known as, and this is a mouthful, the NASA Autonomous Systems Capability Leadership Team, which you can now immediately forget. Just think of that as basically NASA's community of practice on autonomous systems and advisory group to NASA headquarters across the board. So I'm glad to actually see a number of team members that support this overall effort. My deputy is actually here, Danette Allen. I see Isa there. Florence is someplace back in the corner. I don't know who else is out here, but we have a team of people from around the agency that for the past several months has been trying to build a common language, common set of definition, common way of thinking about the overall domain of autonomous systems. And so the slides I have here today represent some of the things that we've put together. I'm sharing them with you to hopefully have a bit of common grounding for us all today and tomorrow as we think about autonomy for future science missions. I'm going to attempt to make this work here. So first off, I wanted to start off by throwing out some definitions. Now, we don't need to have universal agreement. You don't all need to say, oh yes, it's exactly perfectly right for all times, because these are terms that are constantly evolving because people come up with different definitions all the time. I'm just suggesting, at least for today and tomorrow, that we agree to use these in the context of this workshop as a way to facilitate common discussion amongst all of us, especially during the DRMs tomorrow. This is the kind of thing that we've been working on, as I said, within NASA for some time here as a way to allow different parts of NASA, aeronautics and human exploration, science, space technology, small businesses, researchers, engineers, to all be able to communicate about various things. The first is that, when I hear people talk about autonomy, almost instantly I hear people say, oh yeah, that's AI. And I hear other people say, oh yeah, tell me about automation. And I say, well, in fact, these are actually three very distinct terms. AI is not the same as autonomy. It's not the same as automation. I hear people say, oh yeah, you're working autonomy. Tell me about deep learning. And I say, well, I actually know almost nothing about deep learning, but I can tell you a lot about autonomy. And so it's important for us to think about what these different terms mean. To start with, AI is something that has been around for quite a long time. And in fact, the fact that we're in this building, Newell Simon Hall, I think is a testament to how long it's been here. And because Andrew Moore was not able to join us this morning, I thought I would just sort of steal from him and put up his definition of AI, which is AI is the science and engineering of making computers behave in ways that, until recently, we thought required human intelligence. It's a really nice definition because it captures a few things. It's number one, science and engineering. So part of this has to do with how do we build systems that can do things that seemed in the past to be only possible by humans, that is, requiring human intelligence. Now, one thing to understand is that AI is actually a very wide field. It's not just one thing. It's, in fact, something that encompasses many different technologies, many different applications. I mean, everything from machine learning to natural language processing, speech to text, text to speech, expert systems, robotics, vision, almost everything you can think of that has some aspect of being a little human-like, at least in terms of performance or behavior, has in the past been thought of as AI. And as somebody who went to school here at CMU, I can tell you that the people here who work in AI said, oh, AI encompasses everything, includes robotics. But I'll tell you, all robotics people would say, no, robotics includes AI. And so, in fact, there is no single one universal definition. In fact, AI is a very broad thing. It's like talking about air or water or computer science in many respects. Now, automation, on the other hand, is something that we know very well. I mean, everybody who's, well, I'm trying to look at the average age of this crowd here, so I'll speak to some of you. Everybody at one point or another knows how to program a VCR. And my kids say, what's a VCR, okay? Others might say, well, it's a DVR, and maybe that's a little bit better. Others say, well, why would you record anything? You just stream it. But the point is that we are very familiar with the automated operations of things. That is, things that follow a script or a recipe, maybe a command sequence. If you look at the dictionary definition of automation, it's the automatically controlled operation of an apparatus, process, or system by mechanical or electronic devices that take the place of human labor. So automation is something that's not self-directed. It doesn't say, oh, I want to go out and go have lunch today. But rather, it's something that follows a script, as a sequence of things, a pre-planned set of instructions. And that means that a system, in fact, many of our systems that we build, not just for space, but in our everyday lives, will be automated, but not autonomous. So that gets to the real question, well, what is autonomy then? So autonomy, as we've defined it, and this is reflected in the NASA technology roadmaps, is the ability of a system to achieve goals while operating independently of external control. That's it. It has to be able to operate independent of external control. Now, that can be something that can happen over a short period of time, under certain conditions, for a time or event-limited purpose. But the point is that during that period of time, the system is operating independently. And that requires two fundamental things. One is that the system is self-directed, that it's capable of making decisions, it's able to decide what's important, what goals or objectives it needs to try to achieve. And then secondly, it needs to have the ability to be self-sufficient. That is, it has to be able to operate during that period of time without external help. And so unless you have those two characteristics, you cannot have a system that is actually autonomous. I'd like to point out that from a NASA point of view, a system is not just a piece of machinery. In fact, a system is a collection of a lot of things. If you look at the NASA System Engineering Handbook, it includes everything including hardware, software, equipment, facilities, personnel, processes, and procedures. It's everything that rolled together creates the system. And that whole system is the thing that we care about making autonomous. A good example of that is on Curiosity, was mentioned earlier, is a system called Autonav. Autonav is something that allows the rover to drive from point to point. It uses onboard stereo vision, path planning, hazard detection, all on board to make decisions of how to go from point A to point B. It doesn't require any human commanding other than saying, hey, go to this position. And everything in between, all the intermediate waypoints, is something that it can handle by itself. It's able to decide that and be self-sufficient in figuring out how to get from where it is right now to where it needs to go. Another way to think about what is autonomy is to ask the inverse question of what is not autonomy. And as I said already, autonomy is not AI. However, I will point out that a lot of things in AI are used to make systems autonomous. Things like machine learning, perception, a lot of techniques from search, probabilistic methods, classification. All these things are techniques that are used from AI to help make systems operate independently and self-sufficiently. Autonomy is also not automation, just sort of this routine rote execution of scripts or command sequences, although a lot of these systems do build upon automation. They may carry out lower level functions in a purely automated way, but that helps support the overall system's independence and self-sufficiency. And finally, I think it's important to understand that autonomy is not just about making systems adaptive, intelligent, smart, unmanned, uncrewed. These are terms that also get loosely thrown around, and they say, oh, that must be autonomy. It's smart, or it's autonomy because it's intelligent. The reality is that a system, as long as it's able to be self-directed and self-sufficient, I don't care how smart it is by any sort of scale of intelligence. What we care about is that it's able to be capable and operate in some resilient, robust manner when it needs to for that period of time when it is operating independently. Now, it was mentioned earlier at a couple different talks. I was really happy to see some of these points here, but I wanted to go through these to give you a bit more thought, especially as you're going into the DRMs tomorrow, about why is autonomy needed. And I think that as we're talking about future missions, future DRMs, it's important to emphasize that what we care most about are those situations when the only way to do something is through adding more autonomy to a system. That is, for those times, those missions, those tasks where autonomy is the enabling thing, the thing that allows it to actually be accomplished. And so, for example, autonomy is needed when obviously the cadence of decision making exceeds communication constraints. If you don't have comm, or if comm is delayed, or if you have limited bandwidth, and that makes it impossible to actually make the decisions in time or in an appropriate manner, well, then you need to do that on board. Or when time-critical decisions need to be made on board because of factors like communication latency. If you're worrying about entry, descent, and landing on some distant target, and you can't have Earth in the loop because of just communication delay, then obviously you need to be autonomous. You need to do this on board. Similarly, I think it was mentioned earlier about when decisions might be better made using rich onboard data, versus sort of like looking through a little straw from a distance at data that might be old or limited. When you have the ability to take advantage of lots of data, locally, that's a good reason to be more autonomous. I think also along the same lines, when local decision making improves the overall robustness and reduces the complexity of an architecture. I mean, sure, you can create an architecture in some very convoluted way involving multiple COM relays and distributed disruption tolerant networking and all kinds of things to get data from one point to another. But maybe you can eliminate all of that if you just leave everything local, leave everything in the system that needs to be autonomous. And then there's other reasons too, especially those things in other parts of NASA that involve humans, human in piloted spacecraft or humans in aircraft. Sometimes it's better to try to eliminate or reduce the variability that you get because of the fact that we are all ourselves varied in terms of our training, proficiency, our fatigue, whether we've woken up on time or had a really bad night. All those things affect manual control, and a way to sort of level performance is to take some of those variable functions from humans and put them on the side which is not human. I think if you look across the board, one of the interesting things about NASA is that we care about lots of different kinds of systems here. And these are sort of platforms and functions that help support a lot of our missions. In particular, the science type missions that we care about are those that involve obviously launch and landing, especially into deep space, but not limited just to deep space. I mean, landing on the moon is something that's not really truly in deep space, but it's something we care about. The fact is then we care about systems that are in orbit and systems that have to operate on the surface. Lots of different possibilities, and I know that as we're going through the different DRMs, even from the sneak preview we saw earlier, we saw that there is not one universal mission, but lots of different missions, lots of different applications, lots of different functions. And it's important to recognize for every single one of those, there's an opportunity, if it's needed, if it's required to be enabling, to apply more autonomy. Thomas, I don't even know if he's still here, showed this chart, or at least a chart very similar to this chart here, showing the current science fleet that NASA operates, covering everything from Earth science to heliophysics and planetary science and beyond. Very large number of missions. And you look across all these missions, and you ask the question, well, what are the things about this which really drive fundamentally mission design? What are the things here that we care about? And why do we care about them? Well, we care about them because these are things that really affect our choices of being able to add more autonomy or maybe limit the way that we can apply autonomy. So for example, if you think about the unique aspects of this, NASA missions, NASA science missions, they're very few and far between. Many of these are one-off missions. I think it's actually very great to see the fact that at least on Mars, in terms of surface activity, we've had a sequence of rover missions, from Sojourner to MER to MSL to 2020. But that's rare. Most of our missions are one-off. And beyond that, they're also high value. And it's incredibly expensive, incredibly time-consuming to build these missions. Now contrast with this with a lot of the things that are going on outside of NASA's walls today, things that are consumer-facing. These are things that have millions and millions and millions of uses, or maybe millions and millions and millions of platforms. And maybe these platforms are cheap enough for us to be able to afford them. That's radically different than the kind of systems we see in space. And so part of the question is, can we take things that are maybe designed for a mass production consumer level use and apply them to systems which are very few and far between or very high value? Maybe you can, but maybe you can't. It's also the case too that in terms of our missions, we may have high complexity but have to deal with extremely limited communication or very limited computation. And beyond that, it turns out that as a result of all these sort of one-off missions, we have platforms that are very diverse. We don't have a reference mission and say, oh, all surface rovers will look like this thing, or all landers will look like this thing. In fact, we have ones that are customized for every single mission, every single target, and every single thing that we try to accomplish. Because of that, few systems, high complexity, high diversity, limited computing and computation. These are the things that we need to consider because they really have direct impacts about the way we can kind of craft different kinds of missions. I have a chart here that I have to admit that I actually stole from Reed Simmons, who's sitting over there. So credit and apologies at the same time to Reed. And this is really about some thoughts about why autonomy is hard. I think part of it is that the real world, as we recognize, is highly uncertain and changing. Actually Reed found this really great quotation from Don Rumsfeld from 2002, which says there are known knowns, there are things that we know. There are also known unknowns. That is to say, there are things that we know we don't know. But there are also, and this is the important part, unknown unknowns. There are things that we do not know we don't know. And I think this is really important to understand because as we're trying to make these systems more robust and resilient and be able to operate independently, they have to deal with all of these things. They have to deal not just with the known knowns and known unknowns, but they have to deal with the unknown unknowns. And part of that is reflected by the fact that the world is not just an exponential distribution. In fact, it really is a heavy-tailed distribution. That is, the longer you operate, the more that you try to do things, there is still this high probability that you're going to encounter unexpected events. That is, things that you've never, ever seen before. Or maybe things that you'll only see one time and never again. The other thing that's interesting, too, is that all the models that we use to build in terms of state awareness or understanding of what we're trying to accomplish, these are all approximations of the world. Modeling the unknowns, modeling uncertainty is still very hard. And the computation that supports a lot of these models is not yet instantaneous and infinite. I mean, we have limitations on memory, limitations on storage, limitations on how fast we can compute, especially dynamic models that have a lot of different uncertainty associated with those. So because of these reasons, it's important to recognize that one of the difficulties is that the world is extremely, extremely challenging. And if we want to believe that some system is capable of being resilient and robust in the face of that, we have to consider what can we do to make that easier for those systems to function in a manner that's appropriate. I will point out that for those of you who are technologists, you probably recognize a lot of the different boxes on here. These are some of the things. This is not meant to be a representative reference architecture, just to point out that autonomy can involve lots of different things. If you want to have a spacecraft or a rover or a lander be autonomous, you have to worry about planning for that. You have to worry about scheduling. You have to worry about task execution. You probably will need to worry about diagnosis, fault detection, fault protection, fault management, prognostic, state estimation, lots of different things that you combine together into some sort of architecture to deal with this very difficult world. I also want to point out, too, that autonomy is not a widget. You can't just go down to your local Home Depot or Fry's or whatever and say, hey, yeah, I want to buy 3 pounds of autonomy. I don't even know what that means. But the reality is that means that autonomy is system specific. You design it for a specific purpose for a specific system. And that means that you need to think very carefully about, well, is there anything that I could even reuse? Is there anything that I could reuse with a little bit of modification or maybe a lot of adaptation? One of the things that the Autonomous Systems team has done over the past few months then is try to capture some of these building blocks. So we put together an autonomous system technology taxonomy. I believe is referenced from the workshop website, and some of you may have already received copies of this here. It basically describes, at a fairly generic level, some of the core things that we think are important to build these autonomous systems. And the taxonomy covers 4 major areas. The first is situation and self-awareness. These are those things that are needed to interrogate, identify, evaluate the state of the system, the state of the environment. The second is anything that has to do with reasoning and acting. That is, what do you need to analyze and evaluate situations, present, future, past, for decision making, and for directing the actions of that system. The third has to do with collaboration and interaction. This has to do with how you have 2 or more elements of a system. So maybe it's 2 software modules, or maybe it's a robot and a human. How do they work together? How do they interact? How do they transfer information between one another to achieve a defined outcome? And then the fourth area is the area which is probably the hardest today, because this involves the engineering and integrity of these systems. And there's a panel this afternoon where we're going to get into some of the details here. But this has to do with those things that are necessary to actually verify, validate, certify, operationally assure that the systems will perform as intended. We have this much lower level detail taxonomy here, and if you go to the workshop website, as I said, you can find a description of all these different boxes if you're curious, where we have a description of each of the separate boxes and some examples of what goes into them. But I bring this up really to illustrate the fact that making systems autonomous is not just one thing, it's a collection of things. And a lot of these things will be mixed and matched in different ways as you build different systems. It's something to think about, that as we're trying to think about what is a technology gap, for example, it may be the case that 2 different DRMs come up with radically different sets of gaps. And that's OK, because as I said, autonomy is not a widget. It's a system-specific thing. And so it's actually great if we find out, well, this mission needs this set of things, and this other mission needs a whole different set of things. And maybe there's 1 or 2 things in common. But that's actually important for us to understand, because we're trying to figure out not just one mission, but we're trying to understand what are the different things that we need to improve for all sets of missions. I'm just going to wrap up here with some brief thoughts. This is purely my point of view, so this disclaimer here, this doesn't represent anybody else's thoughts except for mine about some of the core things that I think are important for future science missions. One of those is, I think, perception for extreme environments. We've actually sent missions to date to environments which, although challenging, are not as bad as they absolutely could be. But I would contend that we want to send things to places that are as bad as they could be, places that is really difficult to see, places that might require new sensors. If you really want to explore an interior ocean where there is no other illumination other than what you carry, what does that actually look like? I have no idea what sensor is needed for that, but I can tell you it does not exist today. I also think it's important to think about what's needed for reactive science. So if you want to observe and sample dynamic, transient, ephemeral processes, things like plumes or seep or weather, for example, you have to be able to do this decision making on board. You have to be able to react to the phenomenon that you're sensing. That's a really challenging thing. I mean, just like was said earlier, basically trying to capture images of dust devils on Mars. Well, take pictures all the time or try to be more intelligent. And then the third is collective operations. If we want to enable distributed multiple spacecraft missions, and I'll even say the swarm word. I know some of you are fans of the word swarm, but it doesn't have to be swarm. It could be fractionated, it could be distributed, it could be heterogeneous. The point here is that if we want to operate a collection or a collective of things, more than just like one and more than just talking to each one individually, but really able to talk to it as like a team, as an ensemble, that requires fundamentally different designs than we've done to date for missions. Because that requires the different elements of the team to really work together, to really collaborate, to perform things in some coordinated fashion. And with that, it looks like I've got about 8 minutes left for questions.
You did very well. Thank you, Terry. So get your questions primed up. We're going to be moving the mics around the room in a moment. And one other thing, just to give people a little heads up, obviously since Rob Manning is not going to be doing his presentation right after this, he already did his, we're going to move directly into the first panel. So Jen and the first panel should get ready after the Q&A with Terry. That's just to give you his heads up. For now, it's Q&A time. And who has a question for Terry?
So we've had this conversation before. The separation between AI and autonomy, I think I'm in full understanding and agreement of your definitions. But if you go to that last chart, if you flip it back just one, can we really have this conversation without considering AI?
I think the answer is yes. And
why would we want to?
Well, I think this, in some sense, this goes back to Rob's talk earlier, where he's talking about these different levels of whether or not you understand the physical state or the intention. I mean, as humans, we might be satisfied. I'm not saying we should be, but we might be satisfied with a system that's able to autonomously detect and sample, a plume. Maybe it's from Enceladus, or if we actually see plumes, or we actually have the ability to find out, yeah, there are plumes on Europa, maybe we'd be satisfied just to be able to collect samples and return this, without the spacecraft itself being able to understand and reason about why those plumes exist. I think it goes back to the question of fundamentally, what do we want to get out of a mission? On the other hand, it could be very important. I mean, what if you said, well, you today, Mike, you have the opportunity to send a mission to Enceladus, but you can't ever talk to it. You can only get something back. You probably would not be satisfied with, oh, just go out and sample something. You'd probably want it to do more than that because that's the only opportunity you get to actually influence that mission.
I wanted to learn, I think.
And that may be actually a very important thing, that if part of this is being adaptive, being able to learn, whether it's from the mistakes that the system makes or things that happen, again, the unknown unknowns, maybe that's a really core part of that.
Terry, those missions have been flown. You said we didn't want to do. The Galileo probe, the Huygens probe. Sorry. Still.
Finish, Steve.
So I mean, I think we shouldn't spend any time on this AI versus autonomy thing. I think we all know what we want the missions to do. We shouldn't get hung up on the terminology. But I mean, when you say things like you want it to learn, to me, it all goes back to the science, right? So before I would say we want it to learn, I would say, how is that going to improve our science mission? After all, we are the science mission directorate, or most of the people.
Yeah, so I totally agree with that comment. I put these up there primarily because it's something that is, honestly a little frustrating to me when people say, oh yeah, what do you want your missions to do? And I say, oh, I want them to be more autonomous. And they say, oh yeah, so you're using deep learning. And I say, maybe, but because today, unfortunately, out there, there's actually a great blog posting actually by a professor who's here, whose name I now have forgotten, who's just talking about the fact that most people now equate AI with machine learning. And they sort of say, well, they're one and the same. Well, they're not. And I also want to say that autonomy is not just AI and all that. I agree with you. It doesn't really, it's not valuable to focus just on what is the nuanced definition between these things. But the point is, we want our missions to be capable of operating in an independent, self-sufficient manner in order to have better science return. And that's the bottom line.
I don't have I just do want to make a comment on this. I think another way to think about it is in the same way when NASA developed the roadmaps, to think of capabilities versus technologies. And if you define what the capability is, then there's a number of technologies that can achieve the capability, and then you can decide what technologies will allow you to achieve the capability. And,
Yep.
and then these capabilities, I mean, we heard earlier from Rob about there are certain needs of spacecraft to know its attitude or its orientation, and some of them were done with hardware, closed loop, So it doesn't matter how you do it, as long as you achieve the capability. And I think over time, different techniques will emerge, new technologies will come to play to achieve these capabilities in the way we define them. So.
Yep.
So, Terry, given that all models are approximations, and obviously you and I both agree on that, and you want your system to be self-sufficient, is it possible to have autonomy without adaptation?
That's a great question. And I think part of it has to do with, maybe what is the likelihood that it's going to encounter something that it would need to adapt to? So if you're in an environment, let's say for the moment that you happen to be in some environment where there are no unknowns. We know that's not really true, but if there were, then you wouldn't need to adapt because you could be totally self-sufficient, capable of dealing with that. Now, if you then relax it and say, well, okay, what's the likelihood we're going to run into something? Is that something that it could be encompassed with just having more margin? And that's the typical way we do it today. We build something with margin to some performance envelope, and we hope that the margin is sufficient to guarantee that we won't fail something. And maybe that's an appropriate way to do this without adaptation. But I don't know. It's a tough question. I'm not really sure how to really answer that.
Hey, Terry.
Yes.
Thank you very much for your talk. You might be one of the best people to answer this. Maybe others in the room would have a comment. But how do we do INT with autonomy and adaptive systems? I mean, do we even know how to do it? And is it so much more extensive than what we do for non-autonomy systems that we have to seriously consider its impact on cost?
I think that the answer to that question is that we don't know everything yet. I'm very confident that we know some things about testing. And one of the things that we know about testing is that there is no way to exhaustively, systematically test every possibility, which is not necessarily a bad thing. I mean, because that says, well, look, the cost is going to be enormous to do this testing. So what that forces us to do is say, well, what's the alternative? What can we do instead of doing, take a self-driving car and drive 500 million miles, or take, a new landing system and test it end to end? I mean, frankly, even you look at, MSL. I mean, I don't believe that MSL ever tested the complete end-to-end EDL system, but it tested it in chunks, and there was sufficient overlap and analysis that said, yes, it's going to be robust to these set of disturbances.
Do you think that maybe we could introduce autonomy into INT so that we could accomplish it faster?
That's a great question to save for this afternoon's panel, I think.
I thought there was one more there.
I just wanted to say, first off, thank you for the presentation. I thought it was very interesting. Now, we have all this talk about how autonomy is very important, and these systems have to make their own decisions and have to be able to act independently and so on and so forth. And we talked a little bit before about this push and pull dynamic. You know, you tell me what you need to do, and I'll give you the tools you need to make it happen. All of this discussion seems to take for granted the fact that sensors exist that give you the feedback you need. So have you, or has the community taken the time to try to define what those sensors need to look like? So are they just, dumb, non-adaptive, static sensors that are constantly giving you back one kind of data product in one way? Or is it a sensor that is actually parameter agile? It's able to react in some way to its own, or to the environment, independently of whatever decisions the platform itself is making, possibly? Or, is there some third option?
I think that one of the things you've hit upon is that in all the different parts of these building blocks that help make systems autonomous, that there clearly are things that we need that don't exist yet. Sensors is one example, but sensors by themselves, is just a starting point. In fact, most of the systems that I'm familiar with, whether these are robots or vehicles that make use of sensors, don't necessarily care just about the sensor data. What they care more about is perception. So just how do you take that sensor data and turn it into something that's meaningful, whether it's at a semantic level or a geometric level or whatever. And you could actually apply the same sort of discussion to the other parts. Okay, well, it doesn't matter how good your sensors are if you can't process it in time or sufficiently, which means you need appropriate computing. Or none of that matters in terms of perception or in cognition if you can't actually act upon it. So maybe the system itself doesn't have the right actuation or the right mechanism to actually affect the environment. So in each case here, the point is that as we're trying to push for new systems, it's important for us to recognize, what are those things that feed into, the things that make our autonomy, more capable. And if it's sensors, well, clearly we're going to need to invest in some new sensors. I think just, you look around what's happening in self-driving cars today. Would they be where they are today with LiDAR? Probably not. But then at the same time, we recognize that, well, LiDAR is not sufficient. They haven't solved the driving problem just with LiDAR. There's still development going on. So we can't say, oh yeah, all we need for self-driving cars is LiDAR, because it's more than that.
Hi, I just wanted to say I really appreciate the work you're doing here on the taxonomy and the terminology and all that. And even if it's not worth splitting hairs over how much AI content, I want to point out that there's a mirage effect with AI anyway. So once it becomes everyday fare, it just disappears, and like compilers is a good example. Yeah. It started out as an AI thing and nobody blinks an eye at it now. Yep. But what is really important is these terms are so overloaded. You can have people in the same organization having a really intelligent sounding conversation, and they are talking about completely different things and acting like they agree. So the last thing I would like to encourage you to do is spawn a new taxonomy effort that only includes words starting with CO. There's like 20 of them that we all need to understand and use the same way. Thanks.
Okay, great. Thanks.
Super. Thank you so much, Terry. Yeah. And that was brilliant. We're going to start the panel in a second. Just to, as they assemble, just an observation that really taps into the last few comments. 100% agree. Taxonomies and definitions are important in terms of making sure we're speaking the same language. I thought it was a great comment to say, let's not get academic about what's AI and what's autonomy. But at the same time, it's interesting to think of how those definitions, if you exercise the edge of that definition, it's interesting to figure out how AI can be applied in other ways. I'll just give you a quick anecdote. The Canadian Space Agency, I've been doing some AI work with them. They include, as part of autonomy, autonomous medical decision support. So you have a remote mission, it's not the ISS. You can't take an evacuation protocol for a problem. So they're working on adaptive models that models the physiology of every astronaut, gets to know them, and knows what's an exception and what isn't for that astronaut. It's it's an interesting concept. Okay, we are going to move on to the panel. Now the protocol here is that we're going to allow each of the panelists to give about a 6-7 minute presentation. We originally thought 5, but we'll relax it a little bit because they have some really, really interesting things to say. So up to 6 or 7 minutes. That'll just kind of get everyone's thoughts going and also let you kind of situate yourself relative to some of the comments that are expressed. And here's the fun part. This is where we start to do the work that I talked about this morning. This is where now you're engaged, not just Q&A. We're going to work these topics through, and that's what's going to feed all the energy into tomorrow's breakouts. So really energize yourself and get into this. And it's going to kick off with Jen. And we'll move down the line. I encourage the panelists, if you haven't seen the order, make sure John, Bob, David is in that order so you know when to get up. Jen, it's over to you.
Do you want us to use the mic?
I can give you this, and if you want me to step through the slides for you.
Do we have a pointer that we can use, or?
You might be able to click with this.
Okay, we will see. Okay, all right, that works.
So you can click
These work?
there, that one.
To go forward?
Yeah,
Okay,
you're
so it's the
already
left button to go forward if you're first, John. I don't have slides, so. Hi, folks. I'm Jen Gestetic. I am the program executive at NASA headquarters for the Small Business Innovation Research Program, so the SBIR program. I'm going to provide just a real quick bit of framing for what we're hoping to get out of this panel today before I hand it over to our panelists for some of their introductory thoughts. And then we dive into a few questions I'm going to ask just to get the ball rolling on some thinking, but I'd really like for this to be an interactive panel where you guys are not only asking questions but engaging in the discussion. So when Florence and Mike asked me to lead this panel, the primary goal that they had for this part of the discussion was to take the conversation from beyond thinking about the innovative technology, so thinking about autonomy, the new technology and the new capability, and thinking about the means for advancing and adopting and using that technology. So partnering mechanisms that we have and ways that we collaborate, not just between NASA and industry, but NASA and academia, NASA and individual members of the public, through well beyond contracts and grants. So at NASA, we have a long history of funding large missions through big contracts or big grants. But there are also a whole host of other ways in which we've been seeing technology development activities occur beyond traditional contracts and grants. So through things like prize competitions or grand challenges or smaller development efforts through SBIR companies that fit into larger development activities. So we're going to spend some time today during this panel thinking through kind of more of the how we incorporate these innovative technologies, not so much from the technical standpoint, but from the partnering and collaboration standpoint. With that being said, I will go ahead and hand it over to John to kick us off. We had asked each of the panelists to, in order to identify some of these opportunities for collaboration where there might be shared kind of objectives and value, we asked these folks to reflect a little bit from their own vantage point what the opportunities for incorporating autonomy and what the applications in incorporating autonomy from their perspective might be that are well suited to things like partnerships. So they're going to kick off with just some general thinking there, and then we'll dive into the conversation.
It's up to you folks if you would be more comfortable being at the podium so you can see what's going on. It's awkward for you to see your own slides in some cases. It's up to you. You happy there?
I'm good here.
Okay.
Yep.
All right.
Thanks.
So no worries.
All right.
And
Pressure's
to
on.
advance the slide, you click that one.
Okay, great. Thanks. Hi, my name's John Thornton. I'm the CEO of Astrobotic. The reception last night was at our facility down in the Strip District, so maybe a lot of you know about us already, but basically we are building a delivery service to the moon. So we like to think of it as DHL to the moon. We take packages from all over the world, we bolt them up on our lander and fly them up to the surface. And fundamentally, that's stepping stones toward making space accessible to the world. And for us, that's making it regular, routine access to space. So we've got some great partners on our lander, and this is a shot of that lander. This is Peregrine. Can take about 265 kilograms of payload to the surface of the moon. We bolt payloads above and below the decks. And then the lander itself is a single-stage vehicle that's let off as a secondary to fly out towards the moon. And then once we get to the moon, we deploy our payloads. Some payloads will drop and drive. Some payloads will stay attached. We also are going to host the payloads and serve as the local utility. So we're going to provide power and communications for the payloads that come with us. So we've had great partnerships in building this service, and we're very, very excited that we're right now leading the world in payload sales. We have 12 deals so far towards the first mission. Various shapes and sizes all over the place. Mexican Space Agency, for example, is one of our customers coming with us on the first mission. We also have marketing groups and some XX Prize teams, all kinds of different folks flying up to the surface with us. We're especially excited that NASA is getting into the game, going back to the moon, and they came out with a program called Klipsch, which we just submitted the proposal for just yesterday. And if we are selected, we could potentially be a 10-year preferred provider for landed services to go to the moon. And NASA is taking big steps towards making lunar access a more routine, regular event for all of us so we can do science and exploration on the moon. We also have an R&D department that we call Future Missions and Technology with a whole array of capability. We've got some really cool contracts. One in particular that was mentioned a little bit earlier today was flying in and out of caves. We've got a program building a robot that I like to call Batbot, flying in and out of a cave really quickly. We would do it propulsively on the moon. You can do it with rotors on Mars, but that's an extremely challenging navigation problem at high speed. Propulsion is going to run out quick on the surface of the moon. We've got a whole array of other techs, including high-performance computing, really high-performance navigation. We just recently got a $10 million tipping point contract to do precision landing capability and technology. So that will increase the landing accuracy of our missions to within potentially 100 meters of a destination that we target. That's a big improvement over the several kilometers with the otherwise targeted zone. So we're very excited about that and excited to integrate that to our future missions. Oh, maybe that didn't go. Oh. Can you go back one? Yeah. So thinking about autonomy and applications, primarily in the business side, I mean, the first is the autonomous landing that I already mentioned. So I think that's fairly well on its way at the moment. But the next things, the big things that I think are going to be driving the future of space and in particular the moon is the mining applications. So if we can extract lunar water from the moon, we can use that to refuel assets that are going into deep space, and fundamentally begin to sever the tether of required using the resources of Earth to continue to push outward into space. So if we can remove that reliance on Earth resources as we travel out, we can go deeper and deeper and deeper into our solar system and maybe even travel to the next solar system. So if you think about the mining activities that could be required on the moon, it's a huge challenging problem. You'd have to have a lot of surface assets that are going around and extracting the materials and pulling the water out. You need to be able to do fuel transfer and storage, and it's all done in a really challenging environment at the poles, where you've got extreme temperatures. You've got the heat of the sun in the lit parts. You've got the cold liquid nitrogen temperatures in the cold parts down in the craters. So you have to survive, operate. And really, I think one of the biggest challenges from the autonomy standpoint is how do you deal with problems as they arrive? What's your mean time to failure between your extraction robots? So you build a robot to fix your other robots. What happens when the robot fixer breaks? So it's really big, challenging problems. But fundamentally, I think it's our job to solve this. And what that does is it makes it possible, financially possible, to create this business model. Right now, it's way too hard to do this, and it's going to cost way too much. But if we can create systems that are autonomous, that can do this kind of mining and extraction really reliably, we can depend on it for resource extraction from the moon, and we can depend on it for resource extraction from Mars and other destinations as we go. So that's a big stepping stone and building block to go deeper into space. And then of course the surface infrastructure. So anytime you're building anything there, it's going to take a lot of activity, probably a lot of multi-robot work. And realistically, if you're going to do that affordably and in a short time, you're going to need a lot of autonomy to make that happen. And then one thing that I've been thinking about more short term as an autonomy need, we've got a lot of folks that are interested in science and exploration. And one interesting capability to offer to scientists is the ability to survive the night and do long duration missions and go to many, many destinations on the moon. And circumnavigating the moon could be one of those really prime kind of missions to be able to hit a lot of destinations, survive for a really long time, and provide a wealth of data. But you need high-speed navigation, and I know there's a huge body of work at CMU around this right now. But a mission like that can really open up possibilities for our customers that we can then potentially sell for future. Just one last note on the Klipsch program. I'm really excited about how NASA has structured it. So NASA will be able to buy kilograms delivered to the moon. They'll be able to buy kilograms delivered across the moon. And NASA could even potentially buy kilograms of lunar sample. They could just say, hey, go pick up 2 kilograms there and deliver to headquarters. And that's really cool that they're forward thinking in that realm. So that's a quick snapshot, and looking forward to the conversation going forward.
Great, thank you, John. Okay, so Bob is next. Just get this set up for you so you know where you're at.
Awesome.
Keep going.
All right, I'll go ahead and start then. So I'm Bob Touchton, Chief Autonomy Scientist at Leidos. So I'll start with telling you what Leidos is, because a lot of you may not be familiar with that name, but are you familiar with a company called SAIC? Okay, well, like 5 years ago, we fissioned SAIC into 2 companies. The other half of the fissioning kept the name SAIC, so you'll still see that out there. And they were approximately the folks that were working on government teams. And the people that bid on projects are the part that went with the company now called Leidos. Now you're probably asking, well, what does Leidos mean? And that is a made-up word that marketing people really like to get into. And, and I don't know how many millions of dollars this took the company to figure out, but they felt like we found solutions from all the little bits and pieces and pulled it together like a kaleidoscope. And then they pulled Leidos out of the middle of the word kaleidoscope. So that's our name. And you'll see our logo kind of looks like some little chips. That's not a paper airplane. That's actually some little chips from a kaleidoscope. So my role is to look across the company and find out where all the little pockets of autonomy might be, and are we reinventing things or duplicating efforts, or what can we harvest from that? So that makes it a pretty fun job. I also am very much into the autonomy architectures and also interoperability of autonomous capabilities. I kind of see this vision that we're not too far away from the time when everything we buy will kind of be autonomous in its own right or have a certain degree of intelligence. And as you try to assemble a system out of those components, how do you stop the food fights on all of these autonomous capabilities? So I invest a lot of my time in trying to organize that. So we've got a thing we call distributed hierarchical autonomy that kind of layers it into collaborative kind of autonomy, platform management kind of autonomy, and then dealing with individual devices and like sensors, that sort of thing. And then each of those, of course, gets decomposed further. But it embodies this idea of delegation of responsibility, so that something up high in the hierarchy doesn't have to micromanage things down near the bottom. Makes it much easier to swap things out or do tech refresh. So that's what we're trying to prepare for. So we take a kind of a mission-driven approach. Now there are some flaws in that, but we are kind of a company that goes after projects that have a kind of a mission intent to them. So we look for things that, as far as autonomy goes, we track things that are on the higher complexity end of things. They, in a very dynamic environment or a rapidly changing, situation that demands us to push the envelope on autonomy to accomplish it, and cannot be easily accomplished without autonomy. We're also kind of enjoying, let's say, the comfort with AI these days. You know, we kind of had to get through the AI winter where you couldn't call things AI even if they were, because people would get all twitchy. So we're kind of glad to see AI being adopted, although it is frustrating with this thing where AI equals machine learning. You know, we gotta tamp that down a little bit. We love our machine learning, and we do a lot of projects in that area, but it does not equal AI. It isn't. Well, you've already seen that slide from earlier today. Let's see. Did that change? No. Yep. Let's see. This shows three of our biggest challenges right now. We're trying to look at the ability to incorporate new capabilities kind of dynamically, and also with an understanding as these pairings take place, there's an understanding between the parties, the entities, as to the capability. So there's performance models that we're trying to include in that discovery conversation between two new things. And there's some good reasons for doing that, which we can't go into now, but we also have started trying to make the platform that the autonomy is sitting on, kind of a subsystem that we're agnostic to, because although the point was made that there's not just this one autonomy thing, there's a high degree of portability on some of the principles and concepts and functionality. So, we try to take advantage of that by not having tight coupling with the whatever the subsystems are. And also our probably the thing we're most famous for is phenomenology-based technology. So different kinds of sensors, RF, EO, IR, for examples. So this idea of autonomous perception is a big deal for us, because it rides on the coattails of regular perception, before we try to make it more and more self-managing. We also ride on the coattails of some really successful autonomy projects that we get to take credit for along the way, and we've cut our teeth on some of these architectural features and design patterns for architectures that we leverage and as much as we can. Forget about that tether between the ship and the underwater vehicle. I think that was artistic license, because there is no tether. And last is this kind of 5 areas that we've been kind of hitting as a drumbeat that ends up with the one on the far right circles back around to this thing that autonomy is going to be everywhere. We have to thrive in an environment that's not too far from us in our future. And the thing I've been working on the most is this idea of a collaborative autonomy, where it's more than coordinated, it's more than cooperative, it's collaborative, and it's collaboration with the most non-deterministic agents that we have to deal with, and that's the humans, of course. So that's a big part of it. Manned-unmanned teaming is what the Department of Defense likes to call it. But so that's my time. Thanks.
Very good. Thank you so much. Excellent. Okay, we're over to David. We'll move 2 things: the clicker or the mouse, and this thing.
Okay.
Just set up in 1 second, David.
I want to thank Jen and Florence for inviting me to speak. They suggested I give some background on myself. I've spent the last 25 years founding and co-founding space companies. At T-Space, we were hired right after President Bush announced his moon initiative, and NASA wanted to have some advice on how to introduce entrepreneurial principles to a return to the moon. Our basic recommendation was We knew you had to hire Boeing and Lockheed and Northrop Grumman. Why don't you place a side bet of 5 or 10% on commercial initiatives for return to the moon? And that actually morphed into the policy underpinnings for the COTS program. I remember Mike Griffin giving talks to conferences, and he stepped through our white papers basically paragraph for paragraph. Most recently, I was founding CEO of Deep Space Industries. We realized pretty early on that our chief challenge was the cost of propulsion from LEO into deep space. The traditional solutions that we were being offered were costing $4 or $5 million, and for a $3 million spacecraft, that just didn't fit. So we began to develop our own propulsion solutions, and now that provides Deep Space Industries with a very healthy revenue stream. We're about to get into the test firing of our low-cost deep space engine right now. So we asked to also talk about what we would need from autonomy. We'll be poor. You know, we're a private company. We will not have a lot of resources. So we would like our spacecraft to get to work immediately when it arrives on site. There will be things that we already know that we'll be interested in. Because asteroids have a spin, there will be a sunward pole. By default, that probably be where we want the spacecraft to take itself, to maneuver itself to examine the sunward pole. If there is an unusually large crater that may have excavated down to a region where the volatiles haven't been desiccated as much, and so that would be perhaps a secondary target that we'd want the spacecraft to be able to go after on its own. And if the asteroid has 2 lobes like Itokawa, we'd be very interested in finding out whether they are alike or dissimilar. You know, if it was an asteroid that broke apart and came back together, or whether it was 2 different bodies that came together. You know, Christmas for an asteroid mining company would be if one lobe was high in volatiles and the other lobe was high in metals, because then we could use the volatiles to get the metals back to Earth orbit. We also would like, obviously, to have the ability to tell it to go get specific things, but then be able to use its own onboard sensors to skip over what we've selected if it's found something nearby that has more of what we want. And we also want point and thwack. Yeah, the pictures coming back from Ryugu, the Japanese mission there from the surface rovers, show something really unexpected. There's no sand, there's no dust, there's these, to my eye, look like bubbly rocks. We, as a mining company, need to know how strong they are. So, you know, some kind of forceful interaction with the surface that the spacecraft could carry out on its own would also be very useful for us. And finally, a thought experiment. You know, if your spacecraft is relatively inexpensive, say under 25 million, and it's built like we intend to build it with basically an unkillable core that can reboot using a different operating system and perhaps even some different sensors, you would be able to have more than one autonomy system tested on the flight, so that going forward, you know, the pattern in aerospace is if it's flown once, you'll specify it, and it will fly again and again and again. But if you've flown 2 or maybe 3, then you have some choices going forward. You don't have to get you don't have to specify what's flown before to get your grant approved. You'll have a choice of which of the autonomy systems you would fly. That's it.
Thank you very much. That's helpful. So we'll shift into kind of an interactive phase now. Here's what we're going to do in terms of mics, because I think it's important to have 2 mics out there, because that way we can move quickly from question to question. I'm going to unclip this. This is what the panelists are going to use to speak into. And they'll just move it between them depending on who's answering. We'll get both mics out there. And I'm going to, because I'm the MC, I'm allowed to do this. I am going to ask the first question. I think it's.
I had the first question.
You're answering the questions.
I'm answering?
Sure.
I thought I was asking.
Well,
It
you can,
changes
you
everything.
can, you can. That's a first thing. You're moderating. That is true. But you're part of the answers, and I'll tell you why. Is because my question maybe is to cue you up. SBIR and its role in kind of connecting NASA to smaller startups and the innovation there. It's very pertinent, obviously, to the topic on the screen. And here's an important kind of tidbit for all of you. Yesterday, when we were in the Astrobotic labs, having that wonderful reception, we asked John, who, startups are not for the faint of heart. It can be a tough road. And we asked him, well, how did you get through some of these kind of dips in the process? And he said, well, SBIR was a big part of that. And it really is striking, there you are in this room with the lab, it's vibrant, there's stuff going on, they're hiring, and a big part of what got them through that process and into innovating in a way that matters to NASA was programs like this. So that's an observation, and the question I have for you, and then you can do the questions thereafter, is are you seeing a change in NASA in its ability to kind of not suck the oxygen out of the air for these startups? Because it can be quite an onerous thing sometimes to work with a really big entity in terms of processes and protocols and all those sorts of things. Are you noticing a change, and are you optimistic for where that's headed in the future?
Yeah, so I've been leading the SBIR program for 2.5 years, and we've made a concerted effort in the last 2 years to be much more customer focused, thinking about two customers. One, the problem seekers, so people that are on the inside of NASA, that are our subtopic managers that have problems that they need solved. Some of those folks might be trying to solve a specific problem NASA has, and they want to buy 5 of that thing, one to bake, one to break, one to shake, one to fly, one to put on the shelf, right? That's not a huge market, right? It's the NASA market, so it can be hard to actually then turn around and commercialize that sometimes. But those are real needs that NASA has that they can work with small businesses in order to develop. That's one kind of customer, the problem seekers. But then there's also different types of problem seekers, so like the Terrys of the world, that aren't just looking for one specific NASA application, but they're looking at enabling and unlocking and unleashing capability for the agency. So it may not be that there's an immediate near-term project or program application, but it's important to enable the advancement of the R&D and the advancement of the field, and to enable the small businesses to develop their capability. So that's kind of on the problem seeker side, which is one customer. Then there's the problem solver side, which is the other customer. It's our small businesses, right? So our problem seekers aren't going to get any solutions if there aren't companies that want to work with us and don't see beyond the funding, which actually is not large funding. A phase 1 is $125K proof of concept study, and a phase 2 is a $750K 2-year prototype activity. So phase 2 is really where the money is. A lot of companies don't really make much money, and you could talk about this, John, at phase 1. 125K over 6 months is a pretty low scoped effort. But we have really tried to pivot our thinking in the last 2.5 years to be very focused on listening to our customers on both sides, to try to reduce the barriers to entry on both sides, so we can be better connectors through the SBIR program, because that's ultimately what we see our responsibility being, is to connect those two groups together, while also making sure that we have a balanced portfolio in the program. So, phase 1 and phase 2 awards are great, but you're not flying anything. In most cases, there have been exceptions, but you're not flying anything after a phase 2. That's not enough money in the space industry to do something substantial, a phase 1 plus a phase 2. So we've been trying to increase the amount of post-phase 2 funding opportunities we have available to strengthen kind of the infusion and commercialization capabilities that are available through the program to small businesses, and not make them have to just go back to the phase 1 hopper again every time, delaying the development by 1.5 years while they wait for that second phase 2, right? Instead of having to come back to phase 1, how do we actually create more post-phase 2 funding to keep developing the technologies we really need to develop on faster timelines? So yeah, I'd say that's a major priority of ours, and that's been reflected in a lot of the efforts that we've undertook in the last 2.5 years. But we are just one part of the ecosystem, right? To take it back to the panel and to ask a question back to you guys. SBIR may be a critical element. So when I asked John the question of like, when you guys were in your lows, what was really important in order to keep you going, to keep the doors open? And he said, SBIR. I found out we got an SBIR, and that allowed us to keep our doors open. So we play a really important role in helping to provide predictable funding sources to small businesses that are innovating in these places, where they have a chance to continue to come back and kind of us maintain our industrial base a little bit in that way. But there's all sorts of other opportunities they've engaged in, right? There's tipping point opportunities. There's AES Next Step BAAs. There's the ACO, the Announcement of Collaborative Opportunities that comes out of STMD, Small Spacecraft Technologies Program, the Flight Opportunities Program. There's all of these other mechanisms that companies can use to actually continue to move their development forward. And so I'd like to ask the panel a question, since the purpose of this discussion now is to think about how we advance and leverage these technologies and think differently about actually applying them towards science applications, is where we've seen some of these more innovative or different approaches to trying to stimulate progress. Now, Bob, he didn't say this in his introduction, but an impressive stat about Bob is that he worked on both DARPA autonomy challenges. And on one was a finalist, or all of them. I mean, so he's worked on a lot of grand challenge activities, where in that method, we apply a goal that organizations race to that finish line with different levels of resources than you might traditionally see through a traditional contract or grant. But you've also worked through traditional mechanisms. So first question I had was for Bob to kind of share a little bit more on his experience with the Grand Challenge model, which moved forward significantly capabilities in the area of autonomy, sponsored by DARPA in recent years, and then to ask you folks to kind of build on that.
And I would be careful with that mic. It's designed to be about a foot or so away from your mouth.
Great.
So, not so much in the room, but the video and the webcast is getting blown out. So,
Hello.
Yeah.
All right, so, yeah, the DARPA, still too much. All right, the DARPA grand challenges that she's referring to, there was the first two that were running through the desert. You were supposed to go like 130 miles with no human intervention. The paths you were supposed to take were notionally given to you, but they didn't tell you where the road inside that swath through the desert would be. So you had to find the road, stay on the road, and not, go outside the boundaries of that swath. So I was on the University of Florida team on the first one, which was kind of a flop. I mean, nobody got more than 7.5 miles, Carnegie Mellon. And our team finished in the middle of the pack, which was the middle of the pack where it was the group that got out of the sight of the grandstands, but less than a mile. That was my rendering of middle of the pack. So no one saw us tangle the barbed wire around our front left wheel like a yo-yo. That was good. But we were a finalist. And then 18 months later, we did the one where Stanford and Carnegie Mellon won the first 3 spots. Because yes, Carnegie Mellon had 2 teams. We again were a finalist that finished in the middle of the pack, but that meant 23 miles before we got stuck in a dead end that we never had time to implement reverse. So, that's how that one ended. And I've told many people this, that if they had used the right criteria for judging the competition, we actually won, I think, because if it had been miles per dollar invested, we would have blown them out, because we went 23 miles on 250K. So that was quite an accomplishment, I thought. So then I graduated and got my PhD and took a job at Honeywell and ended up being the Honeywell lead on the Honeywell Ford Delphi Urban Challenge, which was, instead of through the desert, this was, in city driving with 30 stunt drivers making noise and creating confusion for the autonomous vehicles. And so we didn't even quite make the middle of the pack of finalists there. I will just say we were not the first team eliminated. But it was, again, it was a great experience, and we learned a lot. So, and then DARPA has gone on to do challenge after challenge. I keep getting closer here. There was the robotics challenge with the humanoid robots. There was manipulator challenges, and they tend to have a strong component of prize-based driver for the innovation. The more recent ones, they have started like having a funded thread for a few of the teams, and then the volunteer teams can come in and participate as well. So I don't know if anybody's cataloged how much of the innovation nuggets from those challenges have made its way into these driverless cars you may see driving around Pittsburgh now, with drivers, of course, but or at least a safety driver. But I know it's pretty high. And in fact, I remember being in the pit area for the Grand Challenge, and a cluster of DARPA people would come around, and we'd make a little circle, and we'd say, do you have any nuggets for us today? And because their business was harvesting capability nuggets. They didn't really have an expectation that somebody was just going to plop something directly and have an autonomous vehicle at the end of that challenge, but they were being a catalyst. There's another model, though, I also wanted to mention, in addition to the prize challenges. Is it all right if I go ahead and, and I don't know if there's an equivalence to this in NASA or not, so, I'd be interested to know if there is. DARPA does a lot of their acquisitions in kind of non-traditional ways. So we get this broad agency announcement that's not broad, it's very specific, but it's also not like a traditional request for proposal type of acquisition. It is completely goal or objective driven, and you have to figure out the requirements yourself. That if I wanted to achieve that goal, how would I write my requirements and statement of work to try to make progress on that? And so that also stimulates innovation, because it's like they come at it as, we don't know enough about this yet to write a requirement specification, but we do know what we want to accomplish. So it's kind of very capability driven, and that's been proven successful in a number of cases. I'll stop there.
And I'd like to then ask John to kind of build on that a bit with some of the models that you have interacted with government and other partners on in order to advance your technology. I know you guys have worked on a tipping point is a specific type of partnership, right? SBIR is a specific type of partnership. The X Prize involvement that you guys worked on is a very specific type of partnership or collaboration. And I think it'd also be interesting to dig a little deeper into when do you decide to participate in which, from the corporate or the company side? Is it, that's a target of opportunity, it exists, so I'm going after it? Or because there's limited opportunity? Or is it more kind of intentional from the alignment of objective side on the private sector side?
Okay, while the mic's going down to John, Jen, I think you've got some really great questions lined up. Did you want to try and just sort of get through those and then open it up to the floor, or would you be open to people asking questions to build on something you've asked, or what would you like?
After John and David reflect on that, this conversation of the models themselves, the collaboration model themselves, totally open to. Okay,
great. So keep that in mind. You folks should be queuing up your thoughts then accordingly. Thanks, Jen. Go ahead, John.
Yes, I just would highlight probably two different models. The first is the Catalyst program. So Catalyst is a public-private partnership between us and NASA. It's no funds exchange Space Act agreement. What it does is it provides funding for NASA personnel to work on our program. So it's a really fantastic way to infuse NASA technology into something that we're trying to commercialize and make readily available for the whole world. And it's been a really positive program for us because we're able to tell our customers and able to tell other folks that are potentially buying or investing or anyone who's backing us that we have NASA working with us. We're not just a fly-by-night operation. we have the credibility of NASA backing us. And when you're a small company, credibility is everything. So Catalyst has been a great program there. The other thing that I'd probably talk a little bit about is the Google Lunar X Prize. So for those that don't know, Google Lunar X Prize was a prize to be the first to fly to the moon, drive 500 meters, and send back HD pictures and video. It ran for 10 years, just recently finished. There was no winner of the X Prize. And I think we were a part of that from the very beginning. We were one of the first teams to throw our hat in the ring. And I think it was, even though no one won, there was some really good things that came out of that. I mean, first it gave a platform for all these young companies to say, hey, we're going to go to the moon and we're not crazy because there's this X Prize thing. It also gave a platform for those groups to grow. But I do think that there were some ways that the X Prize could be improved the next time around. And that is that the prize was not big enough compared to what the cost was to get there in the first place. It created the way the initiative and the way it was structured, it created a lot of emphasis on fundraising. So basically, for many years, it was a game of who can raise the most money, because launches are really, really expensive. And it was really a lot less focused on the technology because of that. For future prizes, what I would advocate for is something that is really a robust, basically super accelerator for developing technology. And that is one where you have a prize that people are excited about. It's got to be something cool to get people jazzed. You get something started, you start with a wide swath of teams, and then you down select, and you provide funding milestones along that path. And importantly, the prize needs to also culminate in a potential business opportunity to really drive that investment. The DARPA challenges were, I think, exactly one of those, right? It's autonomous cars. Of course, there's a huge market there if we can make it happen. Basically, the way I would think about a prize is like a concentrated super accelerator where we're going to get the outcome because we're going to fund each one of the steps to get the teams to the finish line to make sure that we have a great result. And it might be like potentially one of the fastest ways to innovate if you really put the resource behind it to make it happen. So all in all, I mean, there still are a few X Prize teams around, and many of us are now competing for the NASA Klipsch opportunity, which is the first step of commercialization of the lunar landers. So we're really happy that we went through the prize, even though it wasn't won at the end of the day.
Jada, do you have anything to add on any other models? You talked about pods, obviously, earlier.
Well, in terms of prizes, I think for a pure prize, something like the astronaut glove, which can be accomplished in a relatively short period of time by a small group, that's a great model. As John said, with the Google Lunar X Prize, once it was announced, the noise level of teams with great heart but no chance of doing anything rose tremendously. So a series of down selects would be very important for that. For advice to NASA, sometimes the people selecting winners in the competitions are concentrating on what's the sexiest technology we can award this to. On propulsion, NASA has been fascinated with ion propulsion because it has extremely high efficiency. But if you're a business, it really matters whether or not you can deliver that propulsion in a short enough period of time to get a return on investment. So an ion drive that would get you to your destination in 3 years is nice, but for a business, an alternative propulsion, a chemical propulsion system that can get you there in 6 months is better. And it also gets not only the return on investment, it keeps your operational costs down. So sometimes I wonder if you could have more retired industry people on the selection panels, for example, who would be more sensitive to what it would take to move this technology into actual adoption.
Okay, great. We'll open it up now to the floor. We'll keep going, just to give you guys a sense of timing, keep going on open Q&A. I think we'll do a few of these for about another 20 minutes or so. Then we'll take a break. There's food being brought in. Then we'll shift to the second panel, okay? So go ahead.
Thanks. This question is for Bob, and it sounds like you're developing autonomous systems and technologies. So my question is, given that that's not a widget, and given that it's NASA's interest to incorporate these into flight missions that are few and far between and very clearly mission specific, how do you envision the best way is to infuse what you're doing into what we're doing?
Well, this is one of the reasons I put so much energy into the architectures and achieving the high degree of modularity and coming up with these terminologies, and so that if I describe a capability and use certain language, it will be a terminology that you know exactly what we mean. You know, like with maybe not even beyond a taxonomy, maybe even an ontology. Nobody used that word yet, I don't think. But where you actually combine the, explicitly represent the relationships amongst those terms in the taxonomy. That gives us a way to create componentry that is vital to having an autonomous solution, that that only has to be adapted to your mission or your domain. As I mentioned earlier, so much of what we develop is highly portable. I mean, there's been a few things. We developed how to navigate through open waters while following collision regulations of the sea, rules of the road for maritime. That is not portable to any other domain except the sea surface, right? But yeah, well, maybe Europa, but you probably aren't going to have a lot of traffic. But even within that, the decomposition of that problem into like the portion that's flat out reactive collision avoidance, because rule number 2 of the rules of the maritime is don't run into anything. So that's pretty, universal. So that part of it's pretty portable, but the actual rules 3 through the end of it, won't make as much sense unless you're maritime. And the importance of standards is that it gives you a way to compose your solution. So if you're a solution architect, it gives you a way to start cataloging capabilities, and there'll be some holes. And that's where you put your R&D dollars, is filling, the holes while you economize on pulling together the rest of the solution without having to spend your project dollars on that part. So I think that's part of it. I will also confess that I am active in an SAE standards committee. Yes, that's the same people that do your motor oil, but they also have a kind of a high-tech branch called avionics systems, I think it is, or aerospace systems. But anyway, the committee that I'm on is AS for aerospace systems 4. They got a whole bunch of technical committees on the joint architecture for unmanned systems, JAUS, but pronounced JAWS like it's a W. So that's been around for 20 years, trying to have a service-oriented architecture for interoperability. And so it's not just the data that's in an ICD, the interface data, but the protocols on how that data gets exchanged, and discovery on if you're making first contact, what do you need to tell each other to start working together. And it works at large systems all the way down to the componentry, so that if somebody jacks in a new payload into your mobility platform, you can incorporate it into the mission that you're trying to accomplish. And also the idea of starting to have goal-driven autonomy. So if you have an infrastructure and general technology for taking a human intent and turning that into action, something that's actionable, that is highly portable as well. So we're putting a lot of concentration into that. And then I think I mentioned in my opening remarks, we're putting a lot of emphasis into this idea of collaboration and all of the different things that could mean, but especially collaborating with a high number of entities. So if everybody's kind of the same, like insects or geese, well, maybe that's a swarm, but maybe it's heterogeneous and they have to think like a football team. And maybe some of the entities are operated by humans. So the software that we work with is actually puts, there's a chunk of software that runs on the human user interface that allows that entity to be part of this distributed decision-making, planning and decision-making. And then if the human doesn't take their assignment that the group came up with, then they just adapt to that because they're not going to control the human, but they can, it becomes like a decision support system for the human, while it's the actual, autonomy for the software agents and the physical entities, machines or robots. And I will mention one other type of collaboration. The software that we use for that came out of first University of Southern California, and then that grad student became a professor at CMU and brought it with him, and so now it's open source CMU collaborative autonomy software. So when we do these projects, we bring in the university side of it, the small business that professor started to try to extend that capability further. So we bring him and some of his employees on our team. So we've got this, a good example of actual collaboration across academia, small business, large business, and just for fun, we also pull in components from Jet Propulsion Lab. So we use, for example, our resource planner that we use is our rethinking of a re-implementation of Casper, which is a very famous JPL resource planner, which, kind of just closes the loop. We got a little bit for everybody. Thanks.
I want to add just a little bit to your question, Carolyn. I'm blowing up the, sorry everyone online. In the question of how do you incorporate these obviously very fast-moving technologies that are on the outside in the context of NASA missions where one community might get a mission every 10 years, and so they're trying to do everything that they possibly can in that one mission, and risk is obviously top of mind. We heard a lot about risk earlier today. We heard also earlier today that we're 10 years behind. We're chronically 10 years behind. So part of the conversation that I think is one that, we could go so many directions with this panel, but how through partnerships with industry that is more advanced, we can reduce that gap of 10 years behind, right? Maybe now we're 5 years behind or 4 years behind. But it's not, it's that that there are multiple pronged approaches to support some of this multiple bet strategy, right? With the DARPA Grand Challenge, they were looking at multiple bets of how to approach this. Here's the capability we want. People could approach this from a dozen different approaches. Same way with the BAA that you described. Write your own requirements. We're oftentimes at NASA, we write to very specific requirements that we pre-prescribe as opposed to from the capability side. So what is our ecosystem of tools that we have on our side to kind of allow more of those bets to be played in advance of having to make the decision for that once every 10-year mission? And there were some other questions. Mike had one too.
Two questions. Where are the microphones? Sorry. Graham, since you have the same name as me, you go next.
Thank you. So the answer to my question actually started to touch on before. I was interested in where you, as a panel, saw the role of universities in this kind of collaboration between NASA and industry to move towards these autonomous approaches. I'll ask again. So Bob started already to touch on the answer to my question, which was, what is the role for universities in this collaboration between NASA and industry to develop autonomous systems?
My colleague in the room, Claudia, would probably be the best situated to answer this, but she runs the early stage space technology research grants activities. But I will say from the SBIR side, we fund a bunch of STTRs, which require university partnerships. They're usually earlier stage technology development efforts where it requires a university and small business collaboration to try to get things from lab to market, really, and do that kind of technology transfer. And all of these folks have described university collaborations and what they are doing, right? So it is part of, even without perhaps the NASA requirement, to say in STTR it's a requirement. Like I tell you, 49% has to go to a university of that particular contract. But for a lot of these others, they're trying to put together the best team that they can. Do you guys want to talk about any university relationship work? Bob, you already shared.
Yeah, we've had a very successful, long relationship with Carnegie Mellon. We spun out of Carnegie Mellon 10 years ago, or 11 years ago now. So we routinely hire folks from Carnegie Mellon. It's a fantastic partnership. So STTR was one of the more formal ways we've partnered. We've also just been working together for many years and working on the rover systems and the landers and the missions to go to the moon and explore it. So I think fundamentally that partnership's really important because Carnegie Mellon is just doing so much groundbreaking work and research in the area of robotics and space robotics in particular. And in our company, space robotics is our what we like to think of as our core capability. So I think if the businesses get near that raw talent sources and partner on formal programs, I think that's a great way to do it. And even informal things, there could be collaborations that can be done. So I highly encourage the university partnerships.
David, did you have anything?
Just that having moved away from Carnegie Mellon, I am deeply envious of the stream of high quality people that come out of the university. So if you can embed yourself close to a leading university, it's really worth it.
And I'd like to add one more thing that's a slightly different take on that question. This makes me think of the question about talent. And a completely different and interesting model is something that is called the NASA Frontier Development Lab. And SETI folks and possibly some other folks in the room have worked on. This is an interesting approach to bringing talent to space problems that perhaps we would have a hard time hiring, right? So at the Frontier Development Lab takes folks that are postdocs in machine learning, AI, a number of different emerging technology areas, and pairs them with postdocs that have more of a science discipline, whether that's planetary science, earth science, whatever the challenges are of the time, and puts them through an accelerator through the summer to say, if you guys interdisciplinarily work together, how might we be able to apply some of these technologies? If you are a classically trained AI PhD, how can we actually pair you with someone working on small bodies and come up with applications that we might not have discovered otherwise? That not only allows people to spend like a summer working on something that perhaps they are willing to do before they take the high-paying job at Google, right? It's hard for NASA to pay as much as some of the other folks that are hiring in AI and some of those areas to pay, but it also has spun out some possible interesting new applications, as well as changed some talent's view of where they want to work, right? So when they get their head around some of the public sector-oriented problems or some of the scientific or exploration required that they're not getting if they're in a computer science discipline necessarily, it can infect them with space, right? And cause them to want to actually defer where they want to work, right? And help us with the next generation of talent actually spinning in some of these really cutting-edge methods into our domain, which frankly NASA is never going to be able to hire and retain all of the most bleeding edge talent on those topics because we don't pay enough. Yep.
I'm going to need the mic over there. Yeah, I think Bill just wants to add something on the topic of FDL. Then it's over to you.
The interesting thing about the FDL program, as Jen mentioned, first of all, this research accelerator bringing together early career PhDs in machine learning, AI, and their counterparts in various science domains. Each team of 4 has a mentor on the science side, has a mentor on There we go. Now it's on. In addition to the teams, though, the first thing that NASA was trying to investigate through this program was the applicability and viability of applying AI and deep learning techniques to basic research, to science domains. But then the second was public-private partnership. And so FDL also brings in corporate partners who bring in combinations of funding and technology, hardware, software, algorithms, expertise, subject matter experts, et cetera. So the FDL program this past summer included corporate partners like Intel, NVIDIA, IBM, Lockheed Martin, Google. XPRIZE was involved. The Grand Duchy of Luxembourg was involved. So it's been proven to be an interesting way to get science done where, again, there's almost equal monies coming into the program from private industry as from NASA, plus in-kind resources that double up what industry is bringing to the table. And what's attracting industry, just exactly as you mentioned about why some people might even change career objectives by being exposed to this, is the chance to support NASA science and how exciting it is, and exploration and discovery, and what those things can stretch. So happy to talk to people in more detail offline about FDL separately. But
such a good topic. So it's over to Andrew. Yes, I got that right. Just check as we do the Q&A for the remainder of this time that the light's on when you grab the mic, and then we'll do your question, then over here, and then I think we'll wrap it up there.
So I think this question is for Jen. Again, a different kind of collaboration. Luxembourg was just mentioned. Ryugu was mentioned. There's a Japanese spacecraft with a German landed element. The Chinese have a rover on the moon, or had a rover on the moon recently. They're going to go back to the moon. Is there any means for international collaboration on some of this, given ITAR is a thing and presumably autonomy is important in non-science ways? Is there a means or a plan for international collaboration, or are we going to have to remain more or less individual nations dealing with this?
To Terry on some more specifics around the technology development areas there. I will say NASA has a long history of international partnerships, right? We do it on many science missions, on human exploration. Space technology, where I work, is a little bit more difficult to do that because of the reasons that you mentioned. It's a lot harder to say this is your box and you just provide this box and we don't know what's in the box, but we're giving you the interfaces. So from a space tech perspective, it is more difficult, right, on international partnerships. But this is a way that we do business at NASA, collaborating with other international partners. And so there has to be ways that we consider that, right, in the broader conversation. But it becomes a question of technology development versus mission execution, too, as well. Go for it.
We'll have to move this back to you.
Just a quick thing. So the FDL program, for example, one of the things also NASA wanted to encourage was international participation. Of course, they couldn't do the direct funding, but part of the benefit of corporate partners was the ability to bring in international participants. So more than half the participants in the program come from overseas, from South America, from Europe, from Asia. There are a small number, but not insignificant by identity, countries that are excluded from that, as you can imagine. But for the most part, it's an international collaboration. I think last year we had 36 participants from 18 different countries. And actually there were 9 teams, 2 at Ames, 5 at the Institute, and 2 at Oxford University. So it's definitely international, and certainly that element of it was very much encouraged by NASA.
And as the mic is going over to Steve, because I see Steve's hand up, the other thing that is very powerful with some of these open innovation methods that I mentioned earlier, so with prizes, crowdsourcing, citizen science, those in their very nature are typically global endeavors as well. And so when you think about a lot of the activities, for example, that we've run on the NASA Tournament Lab, which is an online crowdsourcing activity where we work through people like TopCoder, which is a global community of coders that are actually developing algorithms and developing software that we are using on NASA missions. We're doing that through individual contributors from around the world participating on some of these crowdsourcing platforms. So the discussion today up to date has been largely focused on organizations or teams kind of participating either through things like FDL or grand challenges or prizes or through contracts or grants. But there's also this whole other area of individual contributors, and especially when you're talking in the area of kind of software and things you can do on your computer. You don't actually have to be building big hardware and bringing it to something to demonstrate. You can demonstrating it by submitting code and then running it against a leaderboard. Those things lend themselves towards broader participation by more people as well, and we have a lot of international participation that happens in those activities.
So I ended up with two questions. So the first question is for everybody on the board, and then the second question is for Bob in particular. And I do want to follow up along the same question that Carolyn posed earlier. Because, autonomy, which is largely embodied in software, not only in software, but largely embodied in software, is a different beast. And it makes the integration more challenging in many ways, and partly because it touches on standards. My question to the board, to the panel, is from your perspective, since on the areas you worked with NASA, what could NASA do to make the interaction? It's a partnership usually between industry and NASA to bring in a capability from outside. From your perspective, what would make this process easier, facilitate it, or even accelerate it?
Terry's chart on all the parts of autonomy, just going deeper and deeper into that specification. And if you're harvesting any modules from flown systems that can be put into that taxonomy for us to reuse, that would be great.
So I think one of the challenges as a small company is that the very large missions and the big flagship opportunities and things that are going on inside of NASA are really, really hard to access. As a small business, it looks like basically a closed door that it's just impossible. What would be really cool is if NASA maybe listed a list of capabilities even that were wanted on those missions, and maybe like on-ramps for small businesses to get involved. We would love to know what NASA wants on future missions. We've got some really anxious guys that are really talented in all of these areas, and we'd love to see if our technology can match up. But it's just so hard to know the inner workings of what those major activities are.
So we have no more questions, but we do have one clarification over here. Oh, you do? You had two questions. All right, go ahead. And then we have a clarification here with Steve right after.
So we talked about architectures, which is one of the essential things related to autonomous systems and software in general. And you talked about what you're doing internally. I would assume, I look at the largest market, which is the autonomous self-driving vehicles. Are we seeing movement towards standardization that enables interoperability of elements of autonomous systems within the industry? I don't know if you can talk to that or not, but this is one of the things, because I see that's where the biggest market, and perhaps there may be things from there that could influence the way NASA and industry interacts in the future.
Okay, yeah, the answer is yes. In fact, SAE has a whole branch of its committee structure devoted to autonomous driving and connected vehicles. So the interactions between those, in both of those realms, have treatment in the automotive sector of SAE. And then when you broaden it to all vehicle domains, air, ground, sea, not yet space, but I have an idea I'm going to pose. That's where JAWS comes in, so the part that I'm working with, and it is all about interoperability. That was the motivation. In fact, one of the things about JAWS, which is now going on like over 20 years old, it was started by the Department of Defense. So its first 10 years was as like a military standard. And it was not started by the S&T or the R&D community. It was started by acquisitions. And in the like in the 90s, they realized that this unmanned system thing was going to take off. You know, it was really not just a phase we were going through. So they said, this is going to be a nightmare. Everybody's going to be bringing in all this technology, and they're not going to talk to each other. And so they created JAWS as a way to prepare for that future. And then after that 10 years, they said, you know, this really shouldn't be a military standard. This should be an international open standard. And they shopped around and finally settled on SAE. And so that's how it kind of got its roots, but now has been broadened. So there's a lot of ground vehicle work in JAWS, but it's not driving on you know, public highways. It's more like convoys and you know, that sort of thing. And so initially it was mainly how to get teleoperated unmanned systems to cooperate, and it with a lot of emphasis down to the component level or device level. So it's like, will this joystick interoperate with that, you know, autonomous Jeep or whatever it is? And then the focus these last, I don't know, 5 or 6 years is now how to prepare for autonomous. So the key to modularity and interoperability is at the interfaces. And it's like, what are the conversations that these different entities have to have with each other to be, you know, successful and do their job? So I actually chair the task group inside this JAWS committee on autonomy. And we're working through what those conversations look like. What does the message have to contain? How do we ping pong back and forth? Because it's not just these like very simple messages you send and you get an act that, yeah, I got it. Sometimes the other party has to ask a question or set a limit or understand a constraint that it has to deal with. So we're building up that part of JAWS as we speak. So we're just about to publish a couple of very straightforward autonomous behaviors, like what do you do if you're conducting a mission with a human on the loop? You know, we call it sometimes sparse supervisory control, but you lose your comms. They get jammed or the radio breaks or you go in a tunnel. What should it do? You know, and there's a way to, through these interface and messages for the robot to understand what it should do when it loses comms. So there was some low-hanging fruit on this somewhere between automated and autonomous behaviors that are about to be published, and then we're you know, trying to jack that up a little bit on a kind of a 6-month drumbeat of expanding that's been standardized. And I will also point out one other thing to the earlier conversation about international. Well, first of all, SAE is an international standard, but we were able to take government-funded work that we did using JAWS, and because you don't have to reveal what that chewy center is of the component itself, you're not revealing any intellectual property or restricted or even government-owned. You're just saying, here's an interface that really worked well. We proved it in the field. So if you can accomplish that capability with a different chewy center, you know, have at it. And so that's a way to work with international partners, or if you're a business and worried about your intellectual property that, you know, that you paid for yourself, you can participate in this ecosystem without having to get into intellectual property issues, because you're compliant with the standard, and so you're good to go.
Great.
Yeah, I just had two quick comments. So first of all, if people go and look at, you know, the reports by, you know, Gartner and Forrester and folks like that, self-driving cars is not the #1 application of AI, at least by the business people who it's their business to size these markets. It's personalization and marketing and robotic process automation, so backroom automation. So just a point there. The second point I wanted to make is the comment on foreign collaborations. I would encourage people who are interested in that to go get good advice from people who have export control training, because it's not there's a lot of misinformation out there. There's a specific set of restricted articles. There's a lot of dual-use technology. Just to give an example, Aspen and Casper, which was mentioned here earlier, has a lot of applications both in the civil space and other applications, let's just say. And it was licensed to the European Space Agency for Rosetta operations. We had installations of it. They used it to operate the Rosetta orbiter mission. So I would not assume that anything is not allowed. You need to, understand the ITAR and more specifically, more likely, EAR rules in order to make your decision.
Great, thank you, Steve. So I think here's my takeaway in closing to sort of the discussion and the great kind of thoughts that have come out of this panel. It's really interesting to think how innovation and collaboration can emerge, not just where, let's say, NASA is the market, meaning it's the bank account that funds the innovation, but it also leads these startups, just nudges them towards a market that's self-sustaining in its own right and gets into sort of the new space economy. And we heard a lot of that too. And for me at least, my obsession, I just can't get over the profit margin here is, a kilogram of aluminum in my hand here is worth $1.80, something like that, maybe $2. That same kilogram in orbit is $8,000. That's a big profit margin if you can get to that aluminum on someone else's dime, which is what orbital debris is. So someone else put it up there. And it's interesting to think as an innovation space, is there a way to get into STM and orbital debris remediation and collection? Just start to move the technology towards something that is more around recycling. Can that debris, if you tap into a really rich field like the Iridium 33 debris field, where everything's on the same orbital plane, super cheap, prograde, retrograde burns to get at it, can you collect that up cost effectively? What if it can get pulverized in orbit down to nanometer scale for accretive manufacturing in orbit? All of a sudden, you've got something that's worth more than its weight in gold. So it's these kinds of innovations, and Jen did me a real favor in bringing up the FDL program. By the way, that exact problem is something that's running in the Frontier Development Lab, which Bill and I are very passionate about at this very minute. Is there a way to optimize flight planning with AI, to use AI heuristics to kind of prune the very complex problem of optimal rendezvous for multiple targets in a single mission to prove it could be a profitable business? And that's the kind of stuff that's really cool, where NASA kind of has visions, pushes the startups along, encourages them to connect to something that ultimately is self-sustaining in terms of a market. So very, very neat conversation. You guys are great in terms of the questions. Thank you to the panel. We're going to take a break. During that time, the students should set up their posters, please, for the session that will occur afterwards, but do that during the break. It's a 20-minute break. Then we're going to do the second panel, which is autonomy in the... Okay, folks, if you want to get your seats, we're going to start the panel momentarily. Grab a chair.
This is meant to be a panel discussion about autonomous systems that have been deployed in the real world, in the wild. So they're tested under real world conditions, have to deal with real world problems. And because a lot of the interest here is really understanding about what's going on outside of NASA, the panelists that we've chosen here, well, Steve can claim JPL is not NASA today, just for a moment. And then he can come back in. But
based on amount of hair, right?
I actually didn't. Dave gets the cookie already.
Oh, I already ate it.
But in any case, the goal here is really to hear about non-NASA work. And that's from the perspective of working on things for other customers or developing technology for commercial markets. In particular, I think it's really of interest to us to hear from the panelists here really some of the things that they've encountered and some of the lessons learned about interacting with the public, with various stakeholders, with regulators, if that happens. And I think it's really of interest to hear opinions about, for these other things, the things that you do, projects you work on outside of NASA, of how do you really approach developing, testing, deploying technology that might be controversial or poorly understood, which I think this domain tends to be in a lot of times because it's unfamiliar, at least to many people today. And with that, what we're going to do is we're going to have some brief introductions from each one of our panelists. I think they've gotten like 2 minutes, but there'll probably be I don't know, 2 minutes someplace on another planet. And then we'll have about 20 minutes of questions from me, and then we're going to open up to questions from you all. So we'll start off with Michael.
Okay, and Mike, could you make sure that your mic is on? And,
Okay.
I'll launch your slides in 1 second. We'll just get
Okay,
you
does
going.
that work?
That does.
Okay.
You are good to go.
Should I hold it closer to my mouth? Okay. So I'm Mike Wagner. I'm the CEO of a company, a CMU spin-off company called Edge Case Research. Thanks for having me on this panel. My research actually started out 20 years ago working with Red Whitaker on some of and Dave Wettergreen on some of the vehicles that we see in the back there. Around 12 years ago, I started working with the DoD on autonomous ground vehicles at that time. And that's when I got really interested in the safety of autonomous systems. DoD was pretty far ahead at that point. This was just as the grand challenges were happening, and we were seeing a lot of interest in different programs. One of the first vehicles that I worked on was this autonomous platform demonstrator, which came out of Carnegie Mellon. And myself and now the co-founder of my company, Phil Koopman, who will be talking tomorrow, put together a safety case for this monster of a vehicle. It isn't quite as much out in the wild as you might want it to be, although it could, as you can tell. And as we talk about safety of these kind of autonomy systems, and as we talk about experiences with regulators and the public, I think we need to look at the different incentives and the different motivations of different kinds of markets and applications for autonomy. We've been talking today quite a bit about exploration missions and things like that. For the Army, obviously, there are very different trade-offs and risk trade-offs, and sometimes it's better to accept risks, even though you might have a lot of uncertainty, because the benefit in terms of survivability or keeping soldiers safe is actually quite clear. So one of the things that I'm interested in talking about today is really how you structure the concept of operations. We heard a little bit about ConOps this morning, which I think is as critical as the technology itself is. So from those defense applications, we went and started Edge Case Research because we had been doing quite a bit of development of testing platforms. And we think that automation for testing, someone brought up the need for AI to validate AI this morning. We think that AI is incredibly powerful for developing test cases and finding test cases that cause all kinds of interesting failure modes that are unexpected. Now, even in simple systems like adaptive cruise control, we can find situations where relatively simple embedded algorithms can fail in unexpected ways. This is very different from what we might call verification. This is sort of anti-verification. But as we go forward with this kind of capability and we get this more and more powerful, what this allows us to do is learn where maybe our assumptions are wrong about these kind of systems, and where we can improve them as quickly as possible. The sort of big challenge that Edge Case is working on now is how to validate the safety of things like convolutional neural networks for perception systems on self-driving cars. So we can definitely talk quite a bit about sort of how, again, those incentives work and what regulation looks like in automotive. I think those are all very, very interesting questions. And sort of how you take these technologies and solve these problems has a lot to do with those. I guess my perspective on this and sort of the idea that I want to introduce to this discussion is that there are really very two different kinds of goals that we're facing here when we talk about safety. One is verification, and this is one that I know many people in this room spend a lot of time thinking about. But the other one that I want to bring up is validation, because as we go into more and more unusual and unexpected environments, we just don't really know how the system should work. And this doesn't just have to do with software complexity, as I kind of show here. It also has to do with the sort of unstructured environments that the autonomy system is operating in, and just how open-ended a mission you have. And from that perspective, automotive is a huge challenge, because we're kind of asking these cars to drive anywhere we might want them to. And in fact, the addressable market for that autonomy grows super linearly as we do that. So it's a recognized problem in automotive that doing this requires a lot of driving or a lot of expenditures or whatever metric you want. Again, I think that to validate simpler systems, we are relying more on established science, but we should frame the idea of validating open-ended autonomy as almost data mining or a very, very empirical kind of exercise. So not to take too much time, but the other point that I wanted to make was that one of the things that I think applications like automotive are leveraging is the ability to go out and do this learning in sort of a responsible way. Right, so you have safety drivers behind the wheel, but you can do a lot of this analysis and validation, say, of perception, even before you put control in charge of the vehicle, right? So there's ideas like that. There's ideas like monitoring low-level assumptions and determining when failures might be happening, even when they don't lead to an accident, and accelerating learning that way. One of the challenges I had when preparing thoughts for this panel was that a lot of NASA missions don't have that luxury, and you're learning things at the same time, and you don't have a very significant safe failure fraction. So it's kind of interesting to look at those different trade-offs, and I'm looking forward to the discussion. Thanks.
Hi, I'm Lut Maliki. I am with Cruise Automation, which is a company that belongs to General Motors, and General Motors is trying to lead the development of autonomous vehicles. It's important for me to go back and tell you that my background is that I started at Jet Propulsion Laboratory. I was there for many years. I ran a group called Quantum Science and Technologies. I was a senior research scientist. And so what we did in the group, we built, developed, conceived sensors, and also used some of those sensors for doing some science. For example, using clocks to test the fundamental constants and their changes, and also building the first laboratory on the ground for NASA on laser cooling of atoms, which now has become a laser cooling laboratory at the space station. What I'm trying to tell you is that I worked as a scientist and as a technologist, and now here at Cruise, I'm working as an engineer. So I finally elevated myself to that level. We have talked a lot about autonomous vehicles, and that's an example of something that has both moving and many, many challenges associated with that. Some of it was mentioned. One thing that I like to share with you is that I was thinking about this. We are trying to make sure that every event that occurs while the car is driving, it can take care of it. It can deal with any kind of eventuality. And of course, to be doing this, we are training cars for millions and millions of miles, trying to expose them to everything that happens. And the other day, and this is a true story, and it's not an anecdote, I was driving, I live in Pasadena up a hill, I was driving up the hill, and in front of me there were two jackrabbits fighting. you've never seen jackrabbits fighting. And the reason it's important is that they would fight and move in one side corner as I was trying to move, then they would run and go fight in the other side. And I was thinking that there is no way that you can capture that in the millions of miles that you're riding. And yet, if you have an autonomous vehicle, you have to be cognizant of this. So where are we with that? Of course, we're not there. The type of autonomy that companies like General Motors are trying to implement is what they call level 5, which means that hands off completely. And the idea is that the car, you call up, it comes, picks you up, and takes you wherever you want. And it has to do certain things along the way. For example, if you change your mind, you ought to be able to change route and so forth. So on the one hand, although it could be connected to all kinds of things, it has to be pretty much autonomous on itself, be the horse that we heard this morning. More importantly, it has to be able to ask the questions such as what if, and answer that what if question. And currently, at the level that we are with AI, we are not there. This business of having agency is what's really needed. And I claim that's the area in the future that would connect the industry with NASA, because having agency at NASA is also important for doing science missions. In particular, you don't want to send, another thing, when at the time when Viking had landed, we wondered what would happen if, as the camera would come in and look at the landing pad, a chunk of it was chewed out. You would say that something took a chunk of that landing pad out, but there was no way that Viking could identify what that was, because it wasn't meant to be looking at opportunistic science. In other words, science that is unexpected. In other words, things that we don't know and we don't know that we don't know. So I think having agency in AI ultimately would help with that. So that's the thesis that I like to put forward. And so with that.
Great. Thanks, David.
All right. I'm David Weddergreen. I spoke to you earlier today. So I just wanted to quickly touch on sort of the autonomy in the wild aspect of some of the projects that I described. I've kind of made my career around not working in the lab, right? If you visit my lab, it's sort of a junk shop with spare parts where we make things and then we do all our work somewhere else. So the slide here, and I think there's a movie that I have no idea how I would make play. Oh, here we go.
Let's say, did you do that?
Just quickly, this is a project funded by the NASA A-STEP program, Life in the Atacama. So we were developing a solar-powered robot that could travel. This is the Atacama Desert. It's navigating autonomously. That is not sped up video. That's actually what the robot does. We spent 5 field seasons in the desert. You can see better than I, but traveling hundreds of kilometers autonomously. We ran, so every time we gave the robot a command, we meticulously tracked how far it went, what happened, did it get to the goal, why did it stop, and we built lots of statistics on hundreds of experiments. We wrote journal papers about how great this was that we could make a robot travel autonomously. And back in the day, in 2005, I was kind of proud of that. I now feel that it's maybe not so much. Next slide. Oop, I do this. So another project pushing maybe on a different aspect of autonomy, in this case, duration. So again, NASA A-STEP, great program. We built a robotic system to explore flooded underwater caverns, cenotes in Mexico. We had no prior model. In fact, these caverns were deep enough that no one had ever dived in them and built a map. So we had a robot going into a totally unmapped environment, starting with blank zeros in its model and building it up as it went. We wanted to study the biofilms that were growing there, but we didn't know where they would be. So the system had to be able to find the walls and approach. It had to decide when to take a sample. We were using modeling of thermoclines and chemoclines as triggers for that autonomous behavior. And these dives would take 6 or 8 hours. And we had nothing to do. We had no tether, so we had no comm. There was, noisy pinging sounds coming from all directions because we were in a cave. So we sat on the shore for 8 hours and watched our watches and wondered what was happening. I was telling someone we probably spent more time worrying about contingency plans and how the robot would be able to get its way out than we did like how it was going to get its way in.
David, welcome to autonomous operations.
Yeah, well, I've been in that nightmare for a long time. So again, it's many hours of totally autonomous operation. Now, I recognize that what Spirit and Opportunity do every day is kind of the same thing. They get one communication, and then stuff happens for a while, and you hope you get communication later. But as I said, now today, we've been talking about self-driving vehicles quite a bit. Waymo, I checked their website last night. They're over 9 million miles of driving. That's a whole lot more than 250 kilometers. 5 billion miles of testing and simulation. And we're still wondering, is that enough? So the question I have in my mind, and I've been worried about this for a while, is if I was pretty happy with 250 kilometers of autonomous navigation in the desert, but it really takes billions of miles for us to be confident in autonomy, how are we going to get there? And I don't know. Well, we'll talk about it. I have some ideas, but I'm not sure.
I'll start with there are no pedestrians on Mars. Okay, so I'm Steve Chen. I head the Artificial Intelligence Group at JPL, and I've been involved in a number of different deployments of autonomy. So in a collaboration with Dan Mandel and others at NASA Goddard, we flew the Earth Observing 1 mission for over a dozen years. 60,000 images acquired under the control of AI software, 3 million commands. It's studied that we've achieved far better than the human command error rate before. We flew all different kinds of machine learning. You can see at the top there, support vector machines, random decision forests, unsupervised learning in the middle there. The stuff on the right we're very proud of. We actually trained the system to classify volcanic plumes and then use geometric information to automatically deliver to the scientists the plume height estimation product rather than raw imagery. At the bottom, you see some of the sensor web deployments where we link together multiple assets in order to allow them to cross-trigger for forest fires, flooding, and so on. And so at the lower right is my baby, which is the automated planning technology, which allowed you to command the spacecraft from your smartphone anywhere where you had an internet connection. And it's not. I also was very privileged to work on the European Space Agency's Rosetta mission, where we deployed AI planning and scheduling technology to automate the early science planning and then also the data management. All the data management was done autonomously. That's a 300 variable decision problem that they have to solve routinely again and again every what's called VSTP, so every 3 or 4 days, in order to make sure that the data doesn't back up on board the spacecraft and they don't lose any. So that's a ground application. And then thinking about more things when they said, what about in the wild? Well, I have to confess, those projects were not really in the wild because, believe it or not, deep space, is, after all the engineers do their job, is fairly benign. So when we tried to do some of this work for autonomous underwater vehicles for the NSF, for SWAT, and also funded by the Keck Foundation, I would have to take my hat off to people like David because it's a lot harder. The ocean is a very hostile place and an unpredictable place. And so we worked on techniques to allow it to track marine fronts and also to do things like find hydrothermal vents. One of the guys on my team was actually on an expedition led by the Alfred Wegener Institute to the Jurassic Massif, about 100 kilometers from the North Pole, the only known hydrothermal vent location underneath an ice cap. And luckily for me, there was someone on my team who 7 weeks on an icebreaker near the North Pole sounded like a fun thing. So I wouldn't have to go. What am I doing now? Well, we're working, this is a literal run from the onboard scheduler for the Mars 2020 rover. At the top, it's scheduling the different activities for medium drive. At the bottom, it's showing the constraint intervals that specify where the different activities can take place. And that squiggly line that you see there is the most important resource. That's the energy level of the battery. So the whole purpose of this onboard scheduler is to improve the operations of the rover, because it's pretty much impossible to predict how long activity is going to take, how much energy they're going to take. And instead of commanding them very conservatively, we want to adjust those plans on the fly. And just my last touch here is there's a lot of other people who are interested in exactly these same problems. So DARPA has a program called Blackjack, which is to put over 100 spacecraft in low Earth orbit with COTS hardware, and they're supposed to all talk to each other, learn, and do, DARPA kind of things. So I'm going to leave with a thesis statement here, which is, I don't know if this is going to be controversial or not, but I think autonomy is all about operations. And so what we're really interested in is the intersection of AI, operations, flight software, and systems engineering. And this is, I think, a key takeaway that we have from decades of work in my lab at working on these missions and getting things into missions. If you don't have that background, you don't understand the complexity of the operations environment. Until you've been there at Saturday and 3 a.m. trying to deliver that medium-term plan to Rosetta, you don't understand how annoying it is to try and I have to re-enter that stuff again. So it's very, very important to, be your own customer in some sense and understand their perspective. So that's all. Thank you.
Great. Thanks very much, everybody. So what we're going to do now is spend about, as I said, 15, 20 minutes talking about a number of questions that I hope to hear from whoever on the panel feels like responding. The first is, given your experience with especially non-NASA projects or working in non-NASA, non-space industries, what do you think NASA can learn from the way that technology, especially autonomy technology, is developed, tested, or deployed?
Well, again, I think that there's quite a bit of work that's going on now in automotive that specifically looks at what's called safety of the intended function, and this is a new ISO standard that's being drafted right now by a bunch of folks who are behind some other software safety standards like ISO 26262. And I think as we start talking about more and more automated kind of capabilities, almost like a behavioral level of autonomy instead of just a safety net kind of autonomy, we need to be not only, again, focusing just on the verification of the technology, but also the validation that the behaviors are suitable for what we want to try to achieve. And so I think we're starting to learn a lot of lessons from things like ADAS capabilities, so driver assistance capabilities, and some early stage autonomy at how we can try to solve these problems. Also, there's quite a bit of background from the DoD world. So there's a DoD standard called MIL Standard 882E, which is very much focused on identifying hazards and trying to come up with mitigations and tracking those mitigations in a fairly systematic way. And so as we go into these new, more and more intelligent kind of capabilities, a lot more of it is about figuring out what the hazards are and validating that we have a reasonable solution rather than I was going to say rather than just using formal methods and whatnot, but formal methods are critical for the mitigations as well. I don't want to understate the value of that.
Great. Other thoughts?
There's a lot of similarities in there, and there's a lot to be learned. But I like to again talk about the things that are dissimilar.
Mm-hmm.
For example, in NASA, we know the resources are time. Something can, been in missions that, it took 5 years, 10 years, 20 years. LISA mission is a good example. On the other hand, the funding is a limitation. In the automotive industry, the funding is not limited per se. What is limited is time. In other words, they're willing to put whatever funding it takes in order to make it, to get the results in time. So what that implies is that it forces a certain boundary condition on you. You have your time crunch, so you go with what you have. You build things on top of each other. Well, what NASA does usually is to treat things as a complete system. For example, what do I mean by that? Right now, there's the AV, there's the sensor system, and things are piled on top of each other, and then we go ahead and drive them around and hope that we manage to train it to work well. That's not necessarily the best way to go. And so learning from that kind of it's not necessarily a mistake, but from that kind of boundary condition is very, very important. If we can, especially since we're talking about science here, if we can combine the science with the rest of it and look at the whole thing as a system in the architecture, include that in there, it's going to be a lot more effective than just saying, okay, I'm a technologist, I'm going to be building this, and we need sensors, so we're going to be building this, and we're going to pile it on top of each other, and we can go. So this, and in the interest of not taking all the time, there are a number of lessons learned that NASA can take advantage of. It's not necessarily all the best things that we do, but the other, the things that we really are doing that we know they're not the right thing, and that's important. And finally, I think NASA will benefit from the economy of scale. You're talking about 17 million cars a year in the United States. And so if you build sensors like we're building, it's going to provide that for NASA. So that's very important.
Okay. Other thoughts, David or Steve?
I guess I would just add quickly that I think the world really is changing, right? This stuff is starting to work. I've spent most of my career explaining why you don't have people or robots washing your dishes for you. But these technologies are starting to work, and it's sort of coming in a wave. So now it's not that it's too risky to try something new, or we've never seen a robot that can operate autonomously before. Those risks, or at least the perception of risk, and I think that's a big part of it, the perception of risk is going down a bit. So that's why, we've been hearing very encouraging things today about, it's not just about risk, it's about all these other things, and we can maybe move forward with some autonomy technologies.
And do you think that perception of risk is just from unfamiliarity or novelty?
Well, yeah, if you see, I don't know, those of you who just recently arrived in Pittsburgh, you haven't seen autonomous cars driving around all over the place. I drive into work, I see 3, 4, 5 of them go by. It doesn't seem so unusual. It doesn't seem so risky anymore. I've had opportunity to ride in a number of these vehicles from different groups, and they drive better than I do. And as soon as you're willing to realize, give up on thinking that you're the best driver, then yeah, you'll go try something else.
Yeah. Actually, along those points, it's interesting to me since I live and work in Silicon Valley, and we're surrounded by self-driving cars all the time. It is true when they first started appearing a few years ago, they were very novel, and now they kind of blend in, although they are obviously very recognizable given they've got LiDAR and cameras all over the place. And what struck me actually yesterday driving to the airport was I was totally fine in ignoring the self-driving car ahead of me until it started driving incredibly erratically. And at that point, I started wondering, is the safety driver drunk? Or is there some fundamental problem with the fact that it was approaching this multi-way intersection and having difficulty with an unprotected left turn? And I concluded it was that.
Were you more or less worried than if it didn't have the LiDAR on top and it was just a human driver?
I was actually only worried not because of the car, the self-driving car ahead of me. I was just worried about the ridiculous line of people behind me that were getting impatient that I was slowing down for it. Right. Any case, let me move on to, unless you had a comment you want to. Next question here then is, I'm kind of curious about what you perceive as the largest non-technical barriers to more rapid adoption of autonomy technology in these different applications. And I'll just give you one little example, and that is in the automotive sector. I actually feel that it's very similar in some ways to NASA because, for example, product lifetimes are very long. A life cycle in automotive is like 7 years, but the life cycle of an actual car that you purchase could be 20, 30 years. And so, technology obsolescence is a big concern for adding new features to cars. I'm just curious, thoughts in general about non-technical barriers?
Let me just say quickly to that point that currently the expectation is that the lifetime is going to be 4 years, at least for the first group of cars coming in. And then maybe beyond that, 7 years. But yeah, that's a big problem, and it has to do, especially when you think about where the cost comes in, and it's clear that the cost of sensors has to go down, the cost of compute has to go down. And that being the case, then you cannot afford to wait too long, because then you're operating something that is too expensive to operate.
I think there's actually an interesting cultural effect that the AV industry is actually going to enable for other industries as well. When we go into some of our customers, we see silos between the safety people and the machine learning people, right? The safety people are dealing with sort of the actuators and the embedded systems and the stuff that we know how to apply, control models to and things like that. And then the machine learning people are off trying to do different things. They're both trying to be safe, right? But there's all of these sort of standards that the safety people follow, and in some cases the machine learning people don't even know how to speak that language. So with all of the interest and progress that the AV industry is making, I think we're going to start to see those two groups come together. And I think that's really important, because those of us that have a little bit of experience, we can look back and see how earlier software safety standards were developed. So we look at MISRA-C, right? So MISRA-C is a language subset that you used. It suggested, I think, originally from the automotive industry, and it doesn't let you do a bunch of things that have been known to cause problems, like use recursion or allocate memory or stuff like that, for very simple embedded systems, just to avoid bugs. And what is it about the rules in MISRA-C that are so magical? There's maybe a couple magical things, but it's mostly from lessons learned and from a bunch of people sitting around agreeing that, the trade-off here is such that it's better just not to do these things. And in the machine learning world, there's a million things like that right now, right? And of all the different groups that all the different potential markets that EdgeCase is looking at, automotive is pulling the hardest, because they have a beautiful application and a life-saving application that they want to implement. And I think that's really making the conversation move much faster than it would have even in like medical or other kinds of things. So anyway, long answer, but eventually this all gets back to some of the conversations that I've seen today, because then they can benefit from those best practices. NASA can benefit from those best practices as they get implemented.
I think Steve had a comment.
One quick comment. By the way, both of those two constraints that you mentioned on the software are both required by the JPL flight software best practices. So in flight software, that's quite typical.
Yep.
I just wanted to mention that, to me, I think the greatest enhancer to the adoption of autonomy technology is greater familiarity. And I think operations people are very used to understanding every aspect of the operations flow and how it's going to affect everything. So it's not like a car where the majority of people who drive a car don't actually know how the car works. They don't know how ABS works. They don't know how these different things work. They just accept it. But I don't think operations people are going to accept that. And therefore, in my experience, when people get familiarity with the technology and they're no longer surprised by, oh my God, why did the planner not put that observation in there, and they understand how to dig into the constraints, understand which constraint ruled out that activity, then they become much more comfortable with it.
So actually, along those lines, is a question for all of you then, is for the respective things that you're doing, whether these are on the commercial side or non-NASA government projects, how do you, best sort of introduce, promote, and engage understanding of these new capabilities? I mean, Steve started getting into that a little bit. I'm curious to hear from the others about how you really get people to understand what is this new thing doing.
Well, a large part is education. I mean, we're a university here, so I guess there's two most direct ways to get that message out. The first is, I talk to people. I try to make good videos and educate through engaging demonstrations. But maybe the more impactful thing is actually all the students that come through here, and not just Carnegie Mellon, but many universities doing this work. But we're graduating 150 students in robotics every year. They all have jobs. They all are going out and they're taking the message to the world.
And more of them to us, David. You need them.
Yeah, well, you can have them.
So how many of those are becoming policymakers? I'm kind of curious.
Well, maybe that happens over time. Yeah. So I mean, maybe the policymaker is the rare one among the robotic technologists. So we have to produce more, and they'll bubble to the top. Yeah.
But I would just mention that we've already conducted our first M2020 end-to-end test using, the ground tools because obviously when the onboard scheduler has variations in what it does, we do actually a structured Monte Carlo so we can present those results back to the operations team, and we're 2.5 years from operations with the simple planner.
Great.
I think it's maybe not such an issue for this crowd, but in automotive, if we do think about the perspectives and experience of people making decisions about certification and regulation, we see that same kind of silo effect that I was talking about. So the well-informed ones are familiar with traditional safety kind of precepts, and aren't very familiar with what's sensitive in machine learning, like how to spot something that's wrong, and I think working those kinds of things out and educating them. There's an XKCD comic about what makes a particular image recognition task really easy or really hard. It can be unintuitive to a lot of people, and so I think to be able to get better incentives in place and better regulation and standards in place, we're going to need to keep doing that kind of education.
Actually, just one more question, and
got
then
it.
we're going to open it all up.
It's your panel, Terry.
One more
You do
question.
what you
One
want.
question. One final question from me, and then we're going to open it up to everybody else here. I think that both Mike and David touched on this in your introductory charts, and that really has to do with collecting "quote unquote" sufficient amount of empirical test data. I'm curious to hear your thoughts about, if it's impossible to actually collect the sufficient amount. I mean, for example, there are estimates from Rand Corporation that you need several 100 million miles of a given system and a self-driving car to then show comparable performance to a skilled human operator, and lots of other examples like that, for most developers, most companies, it's impractical to ever collect enough real-world test data. What does that mean? What's the approach to deal with that? That maybe you just can't exhaustively test everything, especially when there's so many unknowns in the world.
Yeah, so I think this is why I had those two different dimensions, because we have to think about what those data are being used for, and if it's really just for like a statistical black box argument, then that's completely infeasible, because anytime the software changes or whatever changes, then you have to reset. I mean, from first principles, that's what you would need to do, right? Yep. So we have to introduce design information on the verification side. On the validation side, if we know that there are established principles, then we can rely on those established scientific principles when we build a bridge or a flight control surface or something like that. Boeing doesn't need to fly for 400 million miles to know that it's going to be safe, because there have been lessons learned and carefully validated in a scientific way, right? So, but we're talking about something very new and different here, right? This is where the neural networks come in, and so I think as we move forward, we're going to learn ways of developing them that are more efficient. I think that when we go out and we talk about all this data, we actually want to more focus on the things that we don't know, like the squirrels fighting. I wrote that down because I think that's an excellent one, right? And there was
I think it was jackrabbits.
Jackrabbits? Oh, geez, jackrabbits. That's the next one. That's right. But like Reed's chart about the heavy tail distribution, I think that's really what we want to use the data for, right? Is learning about those weird events as rapidly as we possibly can, so we can start to tamp things down.
Although along those lines, I do recall one thing that you said once, which I thought was a wonderful statement. And you said essentially that the world is a really horrible test case generator.
Yeah, because it can be very inefficient, right? I mean,
Right.
most miles are boring.
Right.
So if we just look at if we count it by the number of miles, well, let's go on, a test track and go round and round and round and get the miles. Well, of course that's a counter example to give for sure.
Right.
But at the risk of, let me see if I can inject perhaps some controversy here. I'm shocked that, so both of you guys are talking about lower level control, like with driving and stuff like that. But I would argue that testing is the worst possible way to actually convince yourself that your autonomous system is reliable, because it's the least possible leverage. And as you said, particularly driving around in the actual world, again, This is why people do structured Monte Carlo, because they don't want true Monte Carlo, because the last mile is pretty much like the previous mile, is pretty much like the previous mile. So I would argue that formal methods and automatic code generation, even though they're not the best solution, are the only game in town, because the complexity of the autonomy software is growing exponentially, and you're never going to keep up with the testing. And then I'll quote my colleague Gerard Holtzman, who probably other people said this: testing can never prove that your system is right. It can only prove that your system is wrong.
Agreed. If I can respond.
I mentioned before that I really believe in a Darwinian sense that the systems that we have today are the missing link. The real thing hasn't evolved yet. The real thing is that the same way, I mean, look at any one of us as a driver. How do we do it? We constantly encounter cases while we're driving that we hadn't seen before, but we can respond to that, we can react to that. And that's not because only we've been training for millions of miles. We haven't been driving millions of miles, most of us. The idea is that we gotta have intelligent AI rather than one that just is really data-driven only, and give it this notion of agency that was talked about this morning, and that's really the only way we can achieve this level 5 complete autonomy. And furthermore, just as you said, in the cases like NASA, there's no way we're going to train the spacecraft, before we're going someplace. Well, the only answer to that is again the same thing. We need a system that can ask what if, and answer that question and act on it. And until we have that, we're stuck. We really aren't going to, once you write down the jackrabbits, then the goats are going to come in or something else. You're not going to know it.
So I'm just going to respond to Steve. We can dust it up. So I don't disagree. You can't prove your system will always work from testing. But that doesn't mean you should stop testing things. Right? We've just evolved from the era of getting it to work once was an accomplishment, and getting to it work 10 times means you published a paper about it. So hundreds, thousands, I think we still have many, many tests to run in which the system won't work, and we'll make it better, but we won't make it perfect by testing alone. For sure.
With that, I'd actually like to then switch over to the audience, because you've been so good today, and it's already 4:20-ish or so. So yep. I'm sure there are questions out here.
There are, and the way we're going to do it is a little different. Last time, I'm going to leave you clipped in with a mic. We'll leave that there to move around. We'll move one mic around the audience.
And let's go to somebody who has yet to ask a question today. So actually, I don't recall.
Right to the back. All right, let's get going. And while I'm walking this over, I'm going to say something really important that Florence just said. If we don't get to your question, or if something else comes to mind, and this speaks to her intensity around making the most of this workshop, she wants you to email it, call her, she'll collate it. She wants to hear from all of you, which I think is a testament to her energy again into this. So here we go, first question.
Great. Okay. Just wanted to follow up there as someone who's just coming back from 3 years at Uber, being a machine learning person, worried about safety. I just want to echo some of the things you said there. Definitely the current situation of the safety people doing their thing on the systems they know how to do it for, and the machine learning people doing their thing on the systems they know how to do it for. And everyone wants to bring these two together, and I think, but this is really an opportunity for us. I think we need to reinvent how we think about safety for these kinds of effectively non-deterministic systems. And the thought experiment I always ask myself is, and someone brought it up earlier, you probably got on a plane to fly here. And so I ask myself, why did you get on that plane? And what's interesting, especially in this population, is we pretty much have all the people that could actually read and understand that full safety case, right? But most of us haven't. We just got on the plane because they've been flying a lot, and mostly good things happen. So I think we do have to sort of push the frontiers of How do we test in maybe you can't, there are all kinds of pitfalls of testing, right? Drive a million miles, most of which are useless, right? Those are all pitfalls, but I think we really need to push those bounds, and the reason I think we need to push those bounds is out of necessity, because these learning systems are there. There's no way to hide from that. But also from getting to the proof side, yes, you will not get a proof that the system will not fail. But it's also true that systems for which that proof exists have failed. And so I think we don't want to overstate, which one of these is more effective. We just have to use whichever we can when we can. So sorry, that wasn't really a question, but if comments.
Yeah, if I can just respond. Yeah, so I think that the experience that we've had is that you do want to use a combination of these different effects. I completely agree. And if you split up the autonomy task appropriately, then some of the functions in the autonomous system can very well be handled with some kind of formal methods. I think I would agree with you that when you look at something like autonomous driving or other kind of perception tasks, eventually that formality gives out and you need to do something a little bit different, which I think is what you're getting at when it comes to a different kind of safety. And so, yeah, those are some of the best practices I think that we need to work out.
Steve?
I just wanted to make sure one thing that didn't get left by the wayside. When we talk about formal methods, we also want to allow in the proof by construction, right? So a lot of times the analytical methods, so like all the automated scheduling techniques, it's proof by construction. You know that if you follow this particular process to generate your schedule, it will have these properties.
Questions?
Yes, I have a two-part question, or two-part comments would be useful. So the first thing, and Luke touched upon it, but I think this is an important thing, is designing for autonomy. I was looking at the vehicles. They're not designed for autonomy. They're designed from what we always drove, cars or tanks, so they look just the same. And it just strikes me that it'd be great to get your comments on designing for autonomy. And then the flip side of that is designing the environment for autonomy. And, I can remember hearing a talk many years ago, somebody, maybe it was a Google person or somebody with the drive cars, and saying, four-way stops are hell for these cars because you actually don't follow the rules of the road. So maybe we should get rid of four-way stops. And I thought, oh, yeah. So there's a whole bunch of things that the environment maybe has to deal with when it can deal with it, that we maybe need to look at. And I just like your comments on both aspects of those things, is designing for autonomy, and then what maybe do we need to do in the environment, whatever that is, to change so that we can use autonomy successfully.
Sure. I think you put your finger on it. The autonomous vehicles are not designed for autonomy. They are vehicles that we are equipping with software and sensors, and we want them to operate autonomously. And if you were to start from scratch, you probably would have something different. And this is one of the things that I was saying, that there's opportunity for NASA to learn from that and sort of design that, and with everything in mind. In terms of environment, ultimately, the task of autonomous vehicles, for example, could be made much simpler. The challenge could be much simpler if we could just redo all the rules differently. But the fact is, the challenge is that we have to have the current environment with the most challenging aspect of it, which is the human driver still on the road. We have to have all of that. I mean, we can't do away with that. And so we have to deal with it. But if we are in a position to, again, design not only the autonomy, but also the environment in which it operates, I think that would be fantastic. And again, maybe that's an opportunity for NASA.
I think it's Dave, did you have any comments?
Well, so maybe one of the unique challenges we do face looking at these missions for NASA is that there are a lot of aspects of the problem that you can't structure, right? You can't paint lines on the road, or you can't use that existing infrastructure or the models that you might have of the environment in order to decide how your robot's going to behave. So if you're going to send a robot to Europa that's going to go through the ice, we don't know what's going to be there, right? You're starting tabula rasa, and you have to have a robot that can deal with that. So that, I guess, in some ways makes the problem more difficult for us here.
Right.
I'm going to hand the mic over in a sec.
Yeah, there are no pedestrians, though. I think the pedestrian, I'll take that trade anytime.
I'm going to hand the mic to Rob in a second, but I'm going to just interject with my own question or comment. I think Pat, everyone kind of goes, yes, Pat put her finger on an important point. Cars designed for autonomy, my son works for an autonomous car company. Give an example, it's all our brains can do to just hit the brake and expect all four wheels to brake. But an autonomous car isn't engineered that way. Every wheel can brake independently of the others, and every wheel can be powered independently. So an emergency maneuver isn't a steering wheel thing at all. It slams the brake on front passenger side, creates a pivot point, accelerates with the other wheel. It'll do a maneuver and you'll see it and go like, that just happened. So just break your mindset. It's like the old days when cars were first invented, they stuck a false horse head on the front because no one, so you gotta, interesting though, and this is my comment back to you folks, is I would argue that NASA kind of does have an autonomy mindset. It's almost like it could teach the rest of the industry because it's such it's such a harsh environment that robotics and unmanned kind of almost has always led the way. And the manned missions have often followed. So that's I think Pat really raised a key point. So I thought that was very interesting. Anyway, Bob, over to you.
Well, what I was pondering is that, for autonomous personal vehicles, there's a huge driver having to do with tens of thousands of lives lost every year, reduced to single-digit thousands. I mean, the goal is zero, but probably won't achieve zero, but that's a huge driver. And for other terrestrial systems, there's like getting the warfighter out of harm's way, or the mantra of dull, dirty, dangerous tasks. Well, people shouldn't have to be stuck with those things if machines could do it for them. So, it kind of makes this conundrum, which you started with in your comment, is that I've always looked at space as like the poster child for autonomy, because most of the missions don't have people, at least up in space, and yet I just wondered, are those drivers there, like they are on these terrestrial examples, to be a forcing function for moving towards more autonomy or expanding the application of autonomy? So I just wondered if anybody could reflect on that.
Steve, perhaps?
Well, I think there is, I think the Mars 2020 scheduler is a great example of that. I mean, the forcing function is to run the rover more efficiently because it's a high value asset, and there's not, you get one communications link per day, and it's going to be even worse when we lose the sun synchronous orbiters.
Let me just add again, the purpose of this is, for science support.
Mm-hmm.
And mention that too is the major driver, because you're going to a place that you don't know what you find. Yes, you have information about that. Yes, it's important to find out about the things that you have information about. But there are other things that you don't have information about. And once you discover, for example, we didn't know that there was an ocean out there until we had some spacecraft go out there, and so that took a lot of years and a lot of resources. Now we know there's an ocean. We are interested in going in the ocean. So it'd be nice to be able to manage this kind of a science return by taking advantage of true autonomy. And I'm not just talking about some sensor running by itself or anything, but true autonomy.
I think Jonathan had a question back there.
Yeah, this may be a left field question, but we've been hearing a lot about autonomy of self-driving cars, and then we've been talking a lot about NASA. And there are a lot of other systems where there are autonomy is involved, and we try and apply autonomy. And one thing that comes to mind for me is autonomous train operation. And I was just curious, autonomous train operation seemingly has some similarities to space application also, in that you're dealing with a large system, you're dealing with multiple trains all at the same time. They all have to coordinate with each other. And so similarly, if we were trying to fly, constellations of spacecrafts or something like that, they all have to communicate with each other or with a central node. So it seems like there's a lot of overlap in terms of some kinds of coordination. I was wondering if anyone has done studies and research on that and similarities between those fields.
So it's interesting that you talk about autonomous trains. I encourage you to Google. Deutsche Bahn has a autonomous scheduling system that's reactive and has a deliberative schedule and a reactive scheduler to resolve things like, if they have a train crash or something like that, they have an outage, and it's a very interesting system, very impressive use of on-demand scheduling.
Let me expand that question then to be a little bit broader, because I know we spend a lot of time talking about automotive, and that's probably because half the panel is, hold that, I've got my own mic here, because half the panel spends a lot of time thinking about and working on automotive, but before the big wave, or maybe in parallel with the big wave of self-driving cars, there was all this interest in autonomous drones, especially small-scale ones, and I'm sure that all of you have probably worked on those systems as well. Any thoughts about that market and those applications and some of the challenges there?
I think the challenge is there are different challenges, but one thing that's different is cars. When you think about it, you're moving two-dimensionally, whereas with drone you have the third dimension to worry about.
Sure.
And that changes things with respect to safety, for example, and also opportunities. But yeah, there are, as far as I'm concerned, there's a lot more investment in the automotive section, and so because of that, most of the autonomous systems or that have been put to use have been on automotive. But yeah, drones the same way.
And even there's a couple different kinds of problems. So if we talk about like the air traffic management problem, right? That's one that feels more like the rail and is very amenable to these sort of mathematical models that can be provably correct. As long as you monitor the assumptions of those models, then you're doing great. And that's what a high integrity application in any of those kind of fields demands. If you're talking about picking out a landing site, right, then you're kind of back into the car world again, because you got to perceive it and make a decision based on it. And really, it again comes down to incentives. How important is that? Is an autonomous landing site selector based on the risk?
So we have another question over here, but I'm just going to acknowledge some online questions. Pat's comment kind of kicked off some posts, and it's kind of a pushback, I think, to perhaps my observations, like, wow, NASA's always been kind of robotics first, humans follow. Don't we always design for autonomy? And the pushback is, hold on, are you, the fact that you got these rovers with wheels, maybe you're just stuck in a mindset. What if it's just spherical? What if you just change the form factor of the system? Does the autonomy problem suddenly simplify or change somehow? Does it open up ideas? And I know, I get the point. Close on something I've been thinking about too is, what if the whole autonomy problem of getting from A to B safely, which is a big part of what we've been discussing. What if you just kind of wipe that away and go, you know what, we're just going to make a whole bunch of really cheap, kind of tumbleweed style data gathering systems, any hard surface planet with wind, just let it go, and we'll kind of collect data as we go, and if it doesn't go quite where we want, who cares? There's tons of them. Does it change the autonomy problem in new ways? So we're going to go back to the panel and say, let's be more rigorous in the response to, are we designing to the autonomy opportunity, or are we retrofitting autonomy into preconceived notions of form factor?
So I think that's a really good perspective to bring into it. How can we change the entire system concept in order to maybe make autonomy easier? So,
That was the question I was asking.
well, sorry it took a while to get through.
No, we're trying to get our head around it.
So there, folks might be familiar with some of the inflatable rovers that were developed at JPL, right? So if you have a little robot with little wheels. It can struggle really and spend a lot of time modeling and reasoning about how to get over small obstacles. But if you have big inflated tires, those problems all go away, right? You just roll over the top of it. So changing the scale simplifies autonomy in that case. Now, it introduces a whole bunch of other problems, like how do you get an inflatable rover that can survive? And you still need to do some amount of modeling and understanding the environment to plan for how that's going to operate. But that's true. We could, if we think about the entire system, so the physical system, the environment, and the autonomy all together, maybe we can strike a better balance there and not sort of bite off these really hard autonomy problems when some changes to what we're willing to accept in other parts of the system would simplify.
One final question.
But it's not like these constraints come out of nowhere. So I mean, many times, you know, I've heard this, oh, let's have a whole bunch of small rovers. But fundamentally, the mobility system's goal is to drag around the science payload. So when you get all these instrument people and all these science payload people to produce their 1 kilogram instruments, I mean, the size of the MSL rover and the M2020 rover are driven by the size of the science payload. It's not like they said, oh yeah, let's make this much bigger rover so we can work on Sky Crane. Well, maybe not. I'll see what Rob says. So I think there is a rigorous approach to approaching this, you know, to looking at these problems. I'm not saying that we don't need a diversity of ideas, but I'd say let's keep it in balance.
Again, I like to also suggest that there might be a way around all this by including the science in it as well. In other words, is it possible to perform the science, in other words, get the science information that we want with a large number of tiny sensors instead of one big sensor? Is it possible to do that? I'm not saying in every case we can do that, but the question has to be asked, and that has to be addressed. That what can we do? In other words, you can't keep the science out of the whole thing. The way, at least back in the old days when I was at JPL, you know, you had the science questions and then you went and did the technology on the side. I think they have to be integrated a lot better. And if we can integrate them, we can get more out of them.
Great. So we're going to wrap up with one last question here from Joel. I'm sure there's other hands and questions. Remember, Florence wants to hear from you if you have something that wasn't covered. Joel's going to ask a question. We're going to close the panel at that point and shift immediately to the student lightning talks, which are going to be just fantastic. So go ahead, Joel.
Thanks. So we're talking about NASA science missions here. So if we're going to have an autonomous spacecraft, we're going to allow it to decide itself to collect this piece of data versus that piece of data. So that means the science value of the data has to be expressed somehow. And I assume you've all seen those trade-offs. I'm just curious to hear your experience with that and any lessons learned from that process.
Right. So we actually have a significant amount of experience with that. So just because you have the science data being directed by an autonomous system doesn't mean that you actually literally quantified, oh, the value of this is 7 points, the value of this is 14.4 points. The goal is to allow the science team to interact with the mission in a more civilized fashion. Instead of having to worry about all these assembly language-like instructions, they can express policies. So like in the Volcano sensor web, they could express policies of, if I get 3 mod vocal alerts and this number of GOES vocal alerts in a 2-day period, I want to task and take a thermal infrared image at this priority. The harder question, which I think is a deeper question, it's a long answer, is the question of bias. And so far, thus far, when we've deployed these systems, we have 2 different sets, just like in machine learning. You have some element of the data that's acquired still the traditional or pseudo-random method, so you can measure the bias in your autonomous system's directing of the other measurements. And that's a very weak method, but if you have better ideas, if other people have better ideas, I'm all ears.
So I really appreciated the slide that Rob showed this morning of Dennett's levels there. And I think where the future lies in that 3rd level of systems that actually have some intuition about what they're trying to do. They have some model of the scientific intent, whether that's modeling hypotheses or modeling physical phenomena and how that's expected to evolve. But until we have those models embedded in our intelligent systems, they're really acting like thermostats, right? They're looking for some features. Maybe they're really smart about it and very adaptive about it, but they're looking for some triggers to modulate their behavior. So I think the future of research, and this is what I'm really excited about, is actually putting that intuition in these autonomous systems so that they can make decisions that are really well reasoned.
And defend those decisions. Because I can tell you, you're going to have to the scientists.
No, not defend the
left and
decision.
right.
They have to be able to explain the decisions, and that's part of it, right? If you have that model.
No, I'm going to disagree with you.
This
on
ends
that.
in reinforcement learning.
We were just about to wrap it up on a positive note, and now we're...
It's the first step, but some entity, whether or not it's the designer plus the AI system, needs to be able to defend it.
Okay, so then I think we have to get the person back into the loop. Someone has to.
Just very quickly,
Why stop there?
one benefit of something like that is, again, I mean, most of scientific discoveries are by accident. And if you are going out there to be looking at this, and you know, the thing, the flippant remark I made about the landing gear of the Viking spacecraft, if you're going out there just to look for oxygen, you're not going to find anything but oxygen or lack thereof. And having a system that has intuition allows you to go ahead and maybe discover something that you didn't expect. And that would be the major value of the system that would be autonomous.
On that positive note, I'm going to steal this now. On that positive note, and because I really think you all enjoy hearing from some of the students that are here today, I'd like to thank all the panelists.
Very good.
We will send you all back out into the wild wherever you came from, and this is yours. So thank you.
All right, thank you to the panel. And of course, Terry didn't thank himself, so I'm going to thank him. That was extremely, insightful. So next up, you folks better strap yourselves in, because these students are going to do the lightning talks. Insanely, it's going to be really, very insightful presentations done in a 2-minute time window. So what we're going to do, it's going to be in this order. So the students are in the room. Please take a look at this list right now. Keep track of who you come after and be ready to go, because we want to move through these. At this rate, we're going to be done right on schedule, a little ahead, which is great because it'll give you a chance to interact and network amongst yourself, but most importantly, see the posters that are right outside in the hallway and talk to the students who are just about to present to you. So if you folks are queued up, Andrew's first. Yeah, if you want to get yourselves arranged in a line here, just to emphasize kind of the pipeline of thought coming your way. You guys are... So...
Queue up on the chair.
Sure.
Queue up.
Yeah.
There you go.
Okay. Great. Hi, everyone. My name is Drew Sablehouse. I'm a PhD candidate in mechanical engineering at UC Berkeley. And the work that I have to share with you all today is walking robots with flexible bodies. So I'm actually really grateful to have come right after this talk, because you all have actually justified my PhD thesis. So, so our hypothesis here with including a flexible spine in a walking robot is that now some of this control necessity for like maybe a very rigid robot could be offloaded if the robot can passively adapt to its terrain. And so we, in particular, have been working on these spines based on tension network structures, also called tensegrity systems, where there are rigid parts, like the vertebrae of the spine, held together with cables. And adjusting the lengths of those cables changes the shape of the structure. And so we have, oh, thank you. So we've shown so far that by including the spine in a four-legged robot, the robot can lift and balance on each of its 4 feet. We have some models that match the hardware. And we've also shown that we can actually control the spine. Yeah, there it is, it's moving. So we can control the vertebra of the spine to position it into some of these configurations that lift and balance. And we're currently working on developing gait patterns for the robot to walk using its spine. So please come talk to me. I'd love to hear about what you all might want to put on a robot like this. And then also, if anyone happens to have a postdoctoral researcher position opening in their lab, I am on the market. So please come talk to me.
Right on. Time well spent.
Good afternoon. My name is Steve McGuire. I am at the University of Colorado at Boulder under the direction of Dr. Nassar Ahmed, also with Terry as my mentor. Today I want to talk to you about my thesis work that deals with the problem of what happens when our autonomy isn't perfect. I know all of us want to build the perfect robot that will never fail, and someday maybe we'll get there, but that day is not yet today. So the typical answer has been you throw up your hands and say, human, human, I need a human. And we can, right now, the way that we make that decision is not particularly informed. We have rigid schedules. We have a fixed table. What if we could actually use the properties of the humans we have around us to make better choices about who to ask? So imagine for a second we have this ideal learning robot model where we have, as our tasks are completing, we have this assistant selector that decides who to ask. So big challenges here. One, we need to, how important is it to model humans as unique individuals? Two, what do we need to monitor? There's physiological signals that are already being measured on astronauts, things like heart rate, things for flight physiology. Can we use those? And three, long-term operations. We're not going for a day. We're going to go somewhere for months, years. So I've developed a system using reinforcement learning to learn these parameters that we have 3 levels of implementation. The first is in simulation with fake robots and fake people. The second with real humans and fake robots. And then dealing with some of the practical applications. Why do we care? This allows for more agile missions. We can get away from the scripting and the choreography that are hallmarks of today's human-robot interactions. What this lets us do is leverage autonomy to enable missions that otherwise wouldn't be practical today. So I look forward to talking to you more, and I too will be on the market looking for postdoc opportunities. Thank you.
Hi, my name is Abhishek Kaligi, and today I'll be talking about convex optimization-based approaches for spacecraft robotic trajectory optimization. This work was conducted jointly with my lab mates Andrew Bylard and Ricardo Benali, so I'd like to thank them, as well as our collaborators on the Astrobotic flight software group at NASA Ames. Next slide, please. So the primary motivation behind our work is to come up with algorithms that are capable of providing safe and autonomous navigation capabilities for spacecraft robotic systems. So some motivating examples here are like free flyer robots such as Astrobotic at NASA Ames, where you have these free flying systems operating alongside humans on the ISS and maybe in the future outside of the ISS as well. Satellite resurfacing missions such as Restore-L being developed at NASA Goddard, where you have the satellite chaser satellite come in berth with a possibly uncooperative target satellite and be able to refuel that satellite for extending operation. Next slide, please. So one challenge associated with this is that we have these complicated nonlinear dynamics and all of these actuator constraints, and to be able to provide trajectories that operate in real time. So one tool that we're interested in is convex optimization, which is amenable for implementation for real time on spacecraft robotic systems. Specifically, we looked into sequential convex programming, coming up with an algorithm called Gusto recently for spacecraft trajectory optimization using SEP. So Gusto is an algorithm that has some nice features such as convergence guarantees for nonlinear dynamics. It's capable of handling a broad class of optimal control problems, such as free final time problems and so forth. So next slide. So as some of the examples of what we simulated this on, this is a 12-dimensional free flyer robot operating in a mock-up of the ISS, where this plans trajectories in real time that is capable of avoiding collisions while satisfying the dynamics and actuator constraints for the system. We also implemented this work on the Stanford spacecraft robotic testbed, where you have this simulation of a docking experiment where you have this chaser free-flying robot that navigates through this cluttered environment and grasps with this passive target. So in the future, we want to lift this work off the table experimentally, so we're also scheduled for guest science experiments on the ISS at the end of 2019. So we're working with the Astrobotic group to implement this work on the ISS. That's all for now. Great. Thank you.
And I'm just going to save a little bit of time so they don't all have to say, hey, and if anyone's looking for is there someone in NASA that can just hire all of them in one shot? And okay, over to you.
Hi, I'm Eugene. I'm a PhD student here at Carnegie Mellon, and my research recently has been on belief state planning for reducing uncertainty from terrain relative navigation. So the problem is, if you want your robots to be autonomous and reach your science goals, you need to be able to localize yourself relative to orbital maps, because you don't have GPS and other technology like that on the moon and Mars because it's cost prohibitive to deploy. So there's this technique called terrain relative navigation where you correlate rover perspective imagery to orbital models and maps in order to localize yourself. But the problem is that terrain relative navigation certainty is limited by the quality of your orbital maps. So if you have a lot of noise in your maps, or you're in areas that don't have a lot of terrain features, then you can get lost. Next slide. So our approach for solving this problem is to apply belief space planning to path planning in order to reduce uncertainty from localization. So the illustration on the bottom right shows an example of belief state planning where a robot starts on the left and the circle around it shows how uncertain it is about its position. And the path planned heads toward one of the orange beacons, which reduces its localization uncertainty before heading to the goal in green. Now, for terrain relative navigation, you don't have discrete beacons because you can localize everywhere. So we apply this across the entire map for localization. And we also apply multiple sampling to reduce noise and other errors from digital elevation models. So some results, and I'll have more on my poster, but here we show that compared to shortest path planning, our method is able to find paths that may be a little bit longer than your shortest distance path, but get you to your goal destination with much more certainty. And in situations when there's a lot of noise and errors in your digital elevation models, our method is able to reject the errors and still find optimal paths to your goal.
Excellent, thank you. All right, next up is security alert. My goodness, that doesn't look good. No, you're up.
Okay, only one. Can you try to click the other videos? Or?
Sure.
Okay.
There we are. Is that one a video too?
Oh no. Yeah, that one's a YouTube. That's probably what kicked off the security alert. Okay, well, we'll go without that. I'll play that video at my poster, I guess. So my name is Rebecca Faust. I'm at University of Illinois at Urbana-Champaign, but I'm also a special student at Caltech. I work with Dr. Soonjo Chung and Dr. Fred Hade. My research is in in-orbit assembly from a swarm of component satellites. So I like to call it intelligent connects. So that's what you can see here in the MATLAB image, where the 4 agents come together and dock into an assembly. You can also see it on YouTube, I guess, where we do it with our actual air-bearing platform at Caltech. And then this video in the bottom corner is just another autonomy project that I've worked on, which is an autonomous quadrotor flying in one of the DARPA fast lightweight autonomy challenges. So I've worked on a bunch of different autonomy projects, and I hope you come see my poster so you can hear more about them.
Okay, thank you, Rebecca. Everyone, make sure they go see her video out there. Okay, Felix.
Hi, I'm Felix Gervitz from Tufts University. My advisor is Matthias Scheutz, and I'm working with Terry Fong at NASA Ames. So my research goal really is to develop a computational framework to support coordination in human-robot teams. When I'm talking about human-robot teams, I'm not just talking about the co-located agents working together on some task, but rather a variety of different team structures that can be used to achieve our space exploration goals. So in particular, the focus is on these kind of distributed teams where you might have humans and robots on a spacecraft, let's say orbiting Mars. Then there are planetary rovers there, as well as ground operators back on Earth. And this is kind of this large distributed team that needs to work together to accomplish their goals. They're separated by large spatial distances, timescales. They operate at different interaction modalities, and they all need to work together. So the way we're planning to achieve this kind of coordination is through this formal and computational framework based on the notion of shared mental models. So this is a concept that's been studied for decades in the behavioral literature, human factors, and basically it's this kind of distributed knowledge structure that's shared by all agents on the team to represent different aspects of the task and the team state. So you can see in the table here that the various aspects that would be represented in our framework. So these are things like equipment, task procedures, interdependencies, as well as individual mental models of the teammates. So our framework includes representations of all these things, as well as processes to update the shared mental model state based on inference or perception, as well as processes to adapt agent behavior to be more autonomous based on the shared mental model. So I'd be happy to talk about it more at the poster session later. Thanks.
Great. Thank you, Felix. Brian coming to talk about one of my favorites, quantum.
Thanks. I'm Brian O'Gorman from the University of California, Berkeley. I work with the Quantum Artificial Intelligence Lab at NASA Ames.
Lift a little.
Lift there? Okay. So we work on exploring the application of quantum computing to problems of interest to NASA. Quantum computing has the potential to provide some computational speedups for certain types of problems. But it's realizing that potential is not just a matter of building hardware, but building a lot of software layers on top. So first of all, figuring out what types of problems it can provide a speedup for, and then developing the algorithms and my personal focus, the compilation to effectively and efficiently utilize some very scarce quantum resources in the beginning. And I'd be happy to answer questions later in the workshop.
Great. Thank you very much. We have Catherine.
Hi, my name's Catherine Pavlo. I'm a PhD student here at Carnegie Mellon University. My research is on non-prehensile terrain manipulation for planetary exploration rovers. So what that means, what we're trying to do. This is just a broad overview of the project. So the goal of non-prehensile terrain manipulation is to take existing hardware on your robot and use it for novel purposes. So specifically, we're looking at taking Mars rovers, Moon rovers, other types of rovers, and allowing them to interact with the world by using their mobility systems. So my work is particularly on digging trenches with wheels. In order to actually implement this on a rover, we sort of have to break down the project into a bunch of different levels and implement all of these things. So the first task of the project was to sort of identify potential mission scenarios where these types of actions could be useful, and also identify all of the system requirements you need in order to implement that. Then we needed to develop good models of robot-soil interaction. A lot of the classical models for a lot of the classical terra mechanics models showing the effects of wheel-soil interaction are not actually suitable for really anything but normal driving. From that, we wanted to develop terrain manipulation primitives, so develop primitives that we can use to actually implement in a kinodynamic planner so that we can autonomously plan terrain manipulation. So most of my recent work has been on developing wheel-soil interaction models. If you come see my poster out in the hall, I'll be talking about a model of digging trenches behind a wheel and how we're going to use that to try to draw design insights for rovers.
Fantastic. Thank you very much. We have Ellis next.
All
So I'm going to talk about some of our recent work on cost function design for planning robotic systems. So cost functions are really important in planning because depending on what cost function you choose, that can generate very different behavior. So basically, there are many different ways to specify cost functions, and in practice, though, one common way is actually just to tune this cost function until you are happy with the behavior that it induces. And so the focus of this work is on making that process easier and more robust. Next slide. Thanks. So our framework works as follows. So basically, we first the engineer considers a diverse set of environments. So in this sort of example of navigation, the environments may differ in terms of terrain, weather conditions, and so on. And then for each of these environments, the engineer specifies a cost function, in general, different cost functions, that produce desirable behavior for each of these. And then, next slide, thanks. And then finally, we basically take all this information and we combine it to come up with some kind of common, we infer a common reward function, cost function, which is then robust and generalizes better to new environments. And overall, this process is easier for people to do. So I'm happy to talk about more technical details of how this works during the poster session. Thanks.
Excellent. Thank you so much. And I think, Jacob, you're the last, aren't you?
Yes, sir.
All right.
It occurs to me that the branding is a little harsh, but people like primary colors, right? So hello, everyone. My name is Jacob DeLong. I'm a PhD student studying under Dr. Graham Smith at The Ohio State University. I'm working with Raphael Rincon of Goddard Space Flight Center on my fellowship project. So the objective of this project is to produce a design specification, note not a prototype, but a design specification that we've tested and confirmed for a fully adaptive cloud profiling radar on a 6U CubeSat. So it has to meet the size, weight, and power constraints of that platform and actually be able to achieve full waveform parameter adaptation in real time. Why would we want to do this? Because our previous work in the cognitive sensing lab at Ohio State, specifically in the electroscience lab, has indicated that this fully adaptive sensing paradigm isn't just a flash in the pan. It'll actually let us maximize limited resources and operate at potentially 100% efficiency all of the time, even in highly adverse situations. So, in the past, you design a remote sensing system for a nominal case, right? And so let's say 50% of the time you're overprepared and wasting resources, and then another 50% of the time you still can't function. Well, fully adaptive radar aims to solve that problem by giving you the tools needed to stay active over all of those periods. And of course, we like small sats because small sats are cheaper. So we want to do this by compiling the relevant constraints, so I need to know what the bounding box is. Instantiate the control framework that we already have at Ohio State to apply to this task, and then use the hardware that we have at Ohio State to test this design spec, make sure that it's actually feasible, that it'll produce data, and that we can use it. Go ahead and go to the next slide. Now, the other thing that I work on this project with my advisor, with Dr. Jill Johnson and several others, and it's very nice because this is very synergistic. So once I get to the stage where I have this fabulous design specification, it's going to be great, and I need to know how it's going to behave. The problem with that is that remote sensing simulators tend to be bespoke solutions, like with, so I can't remember who it was, but the comment was that NASA missions tend to be few, far between, and very particular. So it is with radar system or remote sensing system simulators. So what we're trying to do here is give the research community an open source, fully extensible, generalized simulation architecture for fully adaptive, possibly resource constrained, possibly collaborative remote sensing systems. And we're trying to do that in a pretty clever way so that we can actually achieve real generalizability so that it can be reused, and so that it can be reused simply. So it's not this painful, arduous task to pull it off the shelf again, use it for a new system. So I'd love to talk to you about these things in a little bit greater detail at my poster. I appreciate it.
Thank you, Jacob. All right, so listen, here's the next step. is that, of course, the posters are out there. The students you just heard from, listen, you know, it's pretty obvious that's the tip of the iceberg. You can tell there's a ton going on behind those 2 minutes. And hats off to the students. Making a 2-minute presentation is often harder than making a 30-minute presentation. Brilliantly done, all of you. So do go out, network like crazy, talk amongst each other, see the posters. In terms of dinner tonight, it's an open evening because we know you've all made connections today. You're seeing people you need to talk to again. Find your favorite venue. If you can either rely on the AI of Yelp, or grab one of the CMU folks who are either here or one of the students who are local and ask them if you need some recommendations. But enjoy your evening. We will be back here tomorrow at 8 a.m. To kick things off again. And I'm going to close with where I started, which is a big thank you to all of the sponsors, CMU, to the organizers. I thought the presenters did a fantastic job, and I want to thank you because the energy stayed up there the whole time. There was a ton of great discussion. I know you've got your brains buzzing about what we're going to get done tomorrow.